take to navigate this whole job market and find a role that's perfect for you. First things first, why is this so important right now? Well, because the opportunity is just massive. The whole world of information technology and computer networking is always expanding. Seriously, this isn't a field that's shrinking. It's a growing frontier, which is fantastic news for anyone, like you, looking to build a career here. But all that growth brings its own challenge, right? It can kind of feel like you're standing at a crossroads with a dozen different paths stretching out in every direction. Network administrator, security specialist, cloud engineer, it's a lot to take in. So the big question really is, where do you even begin? Well, here's a great landmark to look for on your map, the Cisco CCNA certification. Just think of it like a well-known base camp on your expedition. It's a super respected entry-level certification that tells employers, hey, this person gets it. They have a solid foundation. This is a perfect example of how the right qualifications don't just open doors, they can actually boost your salary right from the get-go. Okay, section 1, your job search toolkit. I love this subtitle. Every explorer needs a map and compass. It's so true. Now that we've got our bearings, it's time to gear up. And for this quest, our tools are the best online resources for navigating this terrain. So let's build your toolkit. So your primary map is going to be a major job site, something like monster.com. This is where you can see the real active job postings out there in the wild. It's your direct window into what companies are actually hiring for right this minute. And of course, every map needs a compass. That's where a site like salary.com comes into play. This tool helps you understand the value of those jobs. It gives you a really clear sense of the pay ranges, so you know what to expect, and honestly what to aim for as you start building your skills. And hey, if you're searching from outside the US, don't worry, we've got you covered. You can find international portals for Monster, and for salary info, check out a site called PayScale. The point is, the right tools are out there for you no matter where your search is happening. All right, so now we have our tools. It's time to actually start the expedition. Let's walk through a super simple step-by-step guide for your very first search. This is where the adventure really begins. So here's the game plan. First, you're going to head to Monster and start with a really broad search, something like network administrator. This just gives you the lay of the land. Next, you start to refine it. Add those specific terms like Cisco CCNA, maybe even filter by your location. Once you've done that, switch gears and pop over to salary.com. Search for titles under information technology, and that's where you'll get those crucial pay estimates. It's a simple process, but it is so powerful. So you've run your search. Now for the fun part, the discovery. We're going to shift from how you search to what you should be looking for, because those job descriptions, they are absolutely filled with valuable clues. And here's a really critical piece of intel. Employers aren't just looking for someone who's interested, they're looking for proof. As you see here, they pretty much always require some kind of industry standard cert or a degree or other qualifications. This is especially true if you don't have a ton of experience yet. And that's exactly why we're doing this research. As you read through those job postings, I want you to be a detective. You're looking for these clues. What job titles keep popping up over and over again? What skills and certs are mentioned constantly? What are the typical salary ranges? And hey, keep an open mind. You might just discover some really cool jobs you never even knew existed. So, what do we do with all this information? It's not just about collecting data. This is the point where all your research gets transformed into a personal, actionable plan. It's time to take what you've discovered and actually start charting your own course. Okay, let's start putting the puzzle pieces together. Think about the raw data from your search. What were the actual job titles you found? Go ahead and list them out. This isn't theoretical. This is the real-world language the industry is using right now. Next up, look for the patterns. What specific skills or certifications kept showing up again and again and again? The market is literally telling you what it values most. That's your study guide, right there. And what about those surprises? Did a job title pop up that you'd never even heard of, but it sounds really interesting? The IT field is so much more diverse than people think, and this discovery phase can open your eyes to possibilities you hadn't even considered. And now we get to the most important question of all. Of all the paths you've uncovered, which ones are you genuinely interested in? Now connect that interest back to the data. What skills, what certifications do those specific jobs require? This is where your personal career quest really starts to take shape. You see, all of this work, the searching, the reading, the note-taking, it all comes together to create something incredibly powerful. These findings, they become the first draft of your personal career map. It's not set in stone, of course, but it's a real, data-driven guide to get you started on your journey. So, you now have a framework for exploration. You've got the map, you've got the compass, and you know how to read the terrain. The only thing left to ask yourself is, what's your first step on the journey? Your expedition is waiting.
All right, welcome to the Explainer. Today, we're going to pull back the curtain on something we use every single second of our digital lives, networking. Seriously, we're going to trace the journey from a single click on your screen all the way to a web page magically appearing. So, let's just dive right in. So, let's just start with a really basic question. How does it all work? You click a button, you try to search, and poof, the whole world is right there. But what's really going on under the hood to make that connection happen in, a fraction of a second? This quote really nails it. Communication is just fundamental to us. And today, almost all of that communication, it runs on networks. They become this invisible utility, kind of like electricity or water, that just connects everything and everyone. So, let's figure out how it works. We're going to build one, right here, right now, from the ground up. Okay, so to understand the whole internet, we're not going to start with the billions of devices out there. That's just overwhelming. Instead, we're going to zoom all the way into the smallest possible piece, a simple conversation. Just two computers talking to each other. So any device that's on a network, I'm talking about your phone, your laptop, even those huge servers in a data center somewhere, has a name. It's called an end device, or a host. Super simple, right? It's just the place where a message either starts or where it ends up. And in this conversation, each device has one of two jobs. It's either a client or a server. Think about it. When you open your browser and search for something, your computer is the client. It's requesting information. The computer on the other end, say at Google, that provides the information, that's the server. It's this constant back and forth, a request and a response. That's pretty much the entire internet in a nutshell. Now that client-server model, that's how most of the internet works. But there is another way called peer-to-peer, or P2P. In a P2P network, there's no dedicated server. Every computer isn't equal. It can be a client 1 minute and a server the next. A really simple example of sharing a file directly between two computers at home. It works for small stuff, but you can probably guess it's not great for big, complicated things. It just doesn't scale up, and security can be a real headache. All right, so we've got the basic one-on-one conversation down. But how do we go from that to connecting a whole building full of computers? Well, we start building a neighborhood. And that neighborhood is called a local area network, or LAN for short. This is basically your home or office network. And it's always made of the same three ingredients. First, you've got your end devices, your computers, phones, printers. Then you have intermediary devices, which is a fancy way of saying your Wi-Fi router or a switch that connects everything. And finally, you have the network media, the physical stuff like Ethernet cables or the Wi-Fi signals flying through the air. Okay, great. We've built our local neighborhood, our LAN. But what happens when you want to talk to someone in a completely different neighborhood, or a different city, or even a different country? How do we connect all these separate little islands? Well, that's where a wide area network, or a WAN, comes into play. The difference is pretty straightforward. A LAN is your local spot. It's small, it's private, and it's usually super fast. A WAN is the big connector. It's the network that links all the different LANs together across cities and countries. These are run by big service providers. And yeah, they're generally a bit slower than your home network, just because of the massive distances involved. So you take your LAN, you connect it to a WAN. Now imagine doing that millions of times over. You connect thousands and thousands of LANs using this giant global web of WANs. And what you end up with is the internet. And here's the really important thing to get. The internet isn't some single entity sitting in a box somewhere. It's not a cloud, it's literally a network of networks. It's this huge, sprawling, decentralized web of private and public networks that have all just agreed to communicate with each other. Nobody owns the whole thing, which is amazing, but it also makes things complicated. But that brings up a pretty big question, right? With billions of devices trying to talk all at once, how does it not just grind to a halt? How does it stay reliable? Well, it's not by accident. The whole thing is built on some really clever rules of the road. Yeah, you can think of the entire architecture of a reliable network as standing on four main pillars. These are the core principles that make sure our online experience isn't a total mess. Let's walk through them. Pillar number 1 is fault tolerance. This is huge. It basically means the network can handle things breaking. You know how if a construction crew accidentally cuts a fiber optic cable, the entire internet doesn't just shut down? That's fault tolerance. It's designed with tons of redundant paths. So if one route gets blocked, your data is smart enough to just find another way to get where it's going. Next up, we've got scalability. This one's pretty easy to understand. It means the network is built to grow. Think about how many new devices connect to the internet every single day. Phones, watches, smart fridges, you name it. Scalability is what allows the network to handle all that new traffic without collapsing under the weight. The third pillar is quality of service, or QoS. The best way to think about this is like a traffic cop for your data. The network knows that not all data is created equal. Your Zoom call or your online game, that's super time sensitive. It needs to get through right now. That huge file you're downloading, it can wait a few milliseconds. QoS is the system that manages all that, giving priority to the important stuff so your video call doesn't get all choppy. And of course, the fourth pillar is security. This is a big one. It's all about protecting the data flowing through the network and the gear that makes it all run. And the scary part is, threats aren't just from some hacker on the other side of the world. They can come from inside too, like a lost laptop or just an employee making a simple mistake. So, because the threats can come from anywhere, good security isn't about having one magical lock. It's about having layers, like an onion. You've got antivirus on your computer itself. Then you've got a firewall protecting the whole network. Then you might have access controls inside the network, and things like VPNs to protect data when it's traveling. Each layer provides another line of defense. Okay, so that's the blueprint, right? Clients and servers, LANs and WANs, and those 4 big pillars holding it all up. But here's the thing, this whole system is never finished. It's constantly changing, constantly evolving, and that evolution is what's enabling some really incredible new trends. Just think about it, all the stuff that feels normal now, BYOD, or bring your own device, where you use your personal phone for your job, collaborating in real time on a Google Doc, storing everything in the cloud, even just telling your smart speaker to turn on the lights. None of that would be possible without the reliable, scalable, and secure network foundation that we've just been talking about. So when you boil it all down, what is all this technology for? It's not just about packets and protocols. The network is fundamentally a system for human connection. And as the tech itself gets faster and smarter and more invisible, the really interesting question isn't a technical one anymore. It's a human one. Now that we've built this incredible connected world, how are we actually going to use it to connect with each other? All right, let's talk about your PC's internet connection. Today, we're going to pull back the curtain on all those settings and really demystify what's happening behind the scenes. We'll show you exactly how your computer talks to the rest of the world. You know that little icon in the corner of your screen, the Wi-Fi symbol with a little computer screen? Yeah, that one. We see it every single day. We connect and we don't think twice. But have you ever really stopped to wonder what's going on back there? How does it all just work? Well, today, we're going to find out. Okay, so for our first stop on this little tour, we need to find the actual physical hardware that gets you online. This is ground zero, the starting point for literally everything that follows. And that piece of hardware has a name. It's called a network interface card, or NIC for short. The easiest way to think about it, it's the physical doorway from your computer out to the internet. And you've probably got at least 2 of them, one for your Wi-Fi and another for that old school Ethernet cable. So how do we find these doorways? It's actually way easier than you'd think. You're just going to pop open the control panel, click on View Network Status and Tasks, and then hit Change Adapter Settings. Boom. That's it. That'll take you right to the main control center for your connection. And voila, here we are. This is the Network Connections window. The big takeaway here is that your computer sees your Wi-Fi and your wired Ethernet connection as 2 completely separate things. They're different pieces of hardware, each with its own icon and its own set of controls. All right, now that we've found our NICs, let's get our hands dirty and start digging into the details. We're going to right-click on the Wi-Fi adapter and select Status to see what kind of juicy information we can uncover. Okay, so right off the bat, you get some really useful info. The SSID, that's just the fancy name for your Wi-Fi network's public name, like My Home Wi-Fi or whatever you called it. And that speed number, super important to know this. That's just the speed between your PC and your router, not your actual internet speed from your provider. It's a common mix-up. Now for the cool part. Go ahead and click that Details button. You'll see something called a physical address. This is also known as a MAC address, and it's a huge deal. Just think of it like a serial number that's literally burned into the hardware. It's permanent, it's unchangeable, and every single network device on the planet has its own unique one. As you're scrolling through all those details, you might spot something kind of weird. It doesn't list just one DNS server, it usually lists two, maybe even more. So what's up with that? Why on earth would you need a backup for this? It really comes down to one word: redundancy. See, DNS is basically the internet's phone book, right? It turns a website name you can read into a number the computer can use. So your PC tries calling the first server in that list. If it doesn't pick up, no problem. It just automatically hangs up and dials the next one. It's a super simple but really clever system designed to keep you connected no matter what. Okay, so that's the scenic route. But what if you want to see all the same info, but a little faster? We can use the command prompt. This is kind of how the pros, the IT folks, check network settings in a flash. So check this out. On the left, you've got that friendly window we were just in. On the right, you have all this text from the command line. Looks intimidating, right? But look closer. The physical address, same. The IP address, same. The DNS servers, exactly the same. It's all the same information, just presented differently. The command line isn't something to be afraid of, it's just another window into the same machine. Now, knowing where to find all this stuff is one thing, but the real power, that comes from knowing how to use this knowledge to fix things when they go wrong. So let's talk about the oldest, most reliable troubleshooting trick in the book. This icon. We've all been there, right? That little globe with the no symbol, taunting you, telling you you're cut off from the world. It's so frustrating. But before you start calling tech support, there's one super simple thing you can try first. Seriously, what I'm about to show you is the absolute number one first thing you should always try when your internet gets flaky or just stops working. Okay, so you're going to go back to that network connections window. Just right-click on the adapter that's acting up and hit Disable. You'll see the icon go gray. Wait a few seconds, then just right-click it again and hit Enable. That's it. This forces your computer to completely reestablish its connection from scratch, and that often clears up all sorts of weird temporary glitches. And this all leads us to the most famous line in all of tech support, doesn't it? Have you tried turning it off and on again? It's a total cliche, I know, but it's a cliche for a reason, because it works an amazing amount of the time. And what we just did, that's the software version of doing exactly that. Alright, before we wrap this up, let's tackle one last question that might be bugging you. We've seen that most PCs have both a wired and a wireless card, but why would anyone ever need to use both of them at the exact same time? I mean, for you and me, one connection is plenty. Your computer is even smart enough to just pick the best one and use it. So what's the deal? Why even have the ability to run multiple network connections at once? Well, the answer really lies in more specialized advanced setups. For instance, think about a computer acting as a proxy server for an office. In a case like that, one network card could be handling all the traffic from the internal office network, while the second card connects to the external internet. It basically becomes a gateway, managing the flow of all that data. So there you have it. That little network icon isn't just a status light, it's the very tip of an iceberg representing a whole control center for your PC's connection to the world. And now you know how to navigate it. So the only question left is, what other hidden parts of your computer are you ready to explore next?
All right, today we are going to get our hands dirty. We're taking a couple of computers, a pair of network switches, and a bunch of cables, and we are going to build a real working network right from scratch. Let's get into it. You know, it really can feel like a bit of magic. You plug a few things in, and suddenly you're online, you can see other devices. But here's the thing, it's not magic at all. It's a totally logical, step-by-step process, and we're going to walk through every single bit of it together. So, first things first, every good project, and I mean every project, starts with a solid plan. Before we even think about touching a cable, we need to know exactly what we're building. And this right here, this is our blueprint. It's our recipe for success. This addressing table tells every single device its unique identity. Think of the IP address like a specific street address for a house. And the subnet mask, well, that's like the zip code. It tells the device what neighborhood it lives in. We're going to keep coming back to this blueprint. Okay, with our plan in hand, it's time to actually build this thing. Before any data can start zipping around, we have to create the physical pathways for it. This is all about the hardware. And honestly, it's about as simple as snapping together some Lego blocks. First, we connect our two switches. That creates the backbone of our little network. Then, PCA plugs into the first switch, and PCB plugs into the second one. And that's it. Our physical network is all cabled up. And this is our first little fist pump moment. When you plug in those cables, you'll see these tiny lights on the switch ports blink for a bit and then turn solid green. That green light is the network's way of saying, hey, I see you, we have a connection. It's a small win for sure, but a super important one. Okay, so our physical structure is in place, but right now it's just a bunch of plastic and copper. It's a skeleton with no brain. So the next step, and it's a huge one, is to give this hardware some intelligence. It's time to configure the digital brains. We're going to start with the PCs. We go right into the network settings and we manually type in the IP address from our blueprint. So for PCA, that's 192.168.1.10. By setting this address ourselves, making it static, we're making sure that other devices will always know exactly where to find it, no guesswork involved. Now the switches are a little different. They don't have a screen or a keyboard, right? So we have to connect directly to their main circuit board using this special thing called a console cable. This gives us a command line interface, basically a direct text chat with the switch's operating system. Before we start telling the switch what to do, we have to get the admin keys. We need to enter what's called privileged exec mode. The command couldn't be simpler. You just type enable and watch the prompt carefully. It changes from a little greater than symbol to a hashtag symbol. That tiny change means we are in. We've got full control. And here's a perfect example of how that works. Our very first command is to give the switch a name, hostname S1, just like in our blueprint. The second, bam, the prompt changes to S1. It's instant feedback telling us the switch understood and did exactly what we asked. So satisfying. Now you might be thinking, wait a minute, why does the switch need an IP address? It's not surfing the web. And you're right, this address isn't for normal data. It's for us, the admins. We assign it to a virtual interface, which is like a secret management door into the switch. This lets us connect to it from anywhere on the network later on. Here's a quick but super important step, security. We can set up what's called a message of the day banner. This is basically a digital keep out sign that pops up anytime someone tries to connect, warning them that only authorized people are allowed. It's a simple but effective little security fence. Okay, listen up, because this next step is absolutely critical. Right now, everything we've done is stored in the switch's temporary memory, the running config. If that switch loses power, all our hard work is gone, poof. So we use the command copy running config startup config to save our work to permanent memory. It's like hitting the save button on a document. Don't ever forget this. All right, the physical build is done. The digital brains are configured and saved. On paper, everything should work, but in the world of networking, you never assume. You test, you verify. It's time to check for a pulse. This is it. This is what it's all about. All that planning, cabling, and typing comes down to one simple question. Can PCA all the way over on one switch successfully send a message to PCB on the other switch? The tool for the job is a beautiful little command called ping, and the concept is just perfect. We tell PCA to ping PCB's address. It's literally like shouting Marco out into the network. And then we just listen. If we hear Polo come back, we know we have a clear path. And there it is, that reply. That single line of text is the Polo we were listening for. It's the sound of success. It's confirmation that our message got all the way there and the reply got all the way back. Our network is alive. And when you look at the final stats, you'll see this beautiful number. Lost equals 0% loss. That's the real prize. It means that every single Marco we sent out got a Polo back. Not a single one got lost along the way. It is a perfect, flawless connection. We can also do one last checkup from inside the switch itself. A command like show IP interface brief is like getting a health report from a doctor. And look at that. The ports we care about are all showing up and up. It's a clean bill of health. All systems are go. Now, I know what you might be thinking. That seemed almost too easy, right? You follow the steps and it just works. But let's be real. In the real world, that first ping often fails. So when it does, what are the usual suspects? Well, it's almost always something simple. It's a typo in an IP address, it's a cable that's not plugged in quite right, maybe the switch isn't even turned on, or a firewall on the computer is getting in the way. The biggest takeaway here is that troubleshooting isn't about some dark art. It's about methodically checking these simple fundamental things. Because a great network is always built on a flawless foundation. All right, let's talk about building a fortress, but not one with stones and moats. We're talking about a digital one. Today, we're going to get into the nitty-gritty of network security, how it works, why it sometimes doesn't, and most importantly, what you can actually do about it. So let's just jump right in with the question. Think about it for a second. Right now, what is the one thing standing between all your personal data, maybe your company's biggest secrets, really your whole digital life, and a complete and utter disaster? You probably picture this big, strong, solid wall, right? A digital fortress. And that's a great way to think about it. But here's the thing. Every fortress has weak points. And you can bet that in the digital world, the bad guys are out there 24/7, just poking and prodding, looking for those tiny little cracks in the wall. So that's where we're going to start. Okay, section 1, our digital weak spots. You can't really defend a fortress if you don't know where the weak points are. So let's go find them. So let's say a threat actor, a hacker, actually gets inside. What's the worst that can happen? Well, the damage usually falls into these 4 buckets. They can straight up steal your information. They can destroy or even just subtly change your data, which is terrifying. They can steal your identity and pretend to be you, or they can just flip the off switch on your services and shut you down completely. The stakes are, well, they're incredibly high. Okay, so how do they even get in? Well, the first weak spot is what we call a technological vulnerability. This is stuff that's baked right into the system itself. Think about the very protocols that make the internet, or the operating system on your phone. Sometimes they just have flaws from the get-go. It's like building your fortress with bricks that already have tiny hidden cracks on them. All right, weakness number 2 is all on us. This is the human error part. We're talking about configuration vulnerabilities. This is basically us leaving the front door wide open. Using a password like password123 or, and this happens all the time, just leaving the default factory set password on a new piece of gear. These are so common, and honestly, they're usually the easiest way for an attacker to just walk right in. And finally, the third weakness is more about the big picture. It's organizational. We call these security policy vulnerabilities. This is when there's just no plan. No written rules for security, no plan for what to do when things go bad, no clear process for anything. It's like having a bunch of guards standing around the fortress, but you never gave them any orders. They don't know what to look for or what to do when an army actually shows up at the gate. It's chaos. Okay, so we know where the weak spots are. Now let's look at this from the attacker's point of view. How do they actually exploit those weaknesses? Let's break down the anatomy of a cyber attack. The attacker's favorite tool is malware, and it's not all the same. You've got your virus, which is kind of like a parasite. It has to latch on to another program to spread. Then there's the worm. This one's scary because it's independent. It can copy itself and crawl across networks all on its own. No help needed. And then, of course, the Trojan horse. Just like the legend, it disguises itself as something you want, something legitimate. And then you, the user, personally invite it right inside your defenses. Tricky stuff. You gotta understand, a real attack isn't just one big boom. It happens in stages. First up is reconnaissance. This is the attacker just looking around, casing the joint, trying to find one of those vulnerabilities we talked about. Once they find a way in, they move to stage 2, access. This is the break-in. They're inside the walls. From there, they can do all sorts of nasty stuff, including the third stage here, a denial of service attack, where they basically just make it impossible for you to use your own network. So how in the world do they pull off a massive attack like that? Well, one of the most powerful ways is with something called a botnet. It's pretty sinister. A hacker infects thousands, sometimes millions of computers around the world with malware, turning them into a secret army of zombies. Then, with a single command, they can order that entire army to attack one target all at once, flooding it with so much traffic that it just collapses. It's a brute force coordinated assault. Okay, that was a little dark, I know. We've seen the threats, we've seen how the attacks work. It can feel pretty overwhelming. But don't worry, because now we're going to pivot. We're going to talk about the solution. It's time to talk about building a layered defense. You've probably heard the saying, the best defense is a good offense. Well, you can just throw that out the window for cybersecurity. Here, the best defense is more defense. It's a concept called defense in depth, and it is absolutely crucial. There is no one magic product that will save you. Instead, you build layers, just like a medieval castle. You've got the moat, then the outer wall, then the inner wall, then the guards and the keep. The idea is simple. If one layer gets breached, you've got another one right behind it, ready to stop the attack. So, what are these layers exactly? What do they look like in the real world? Let's open up the toolkit and see what we're working with. Okay, one of the most fundamental layers is all about controlling who can get in and what they can do. It's a framework called AAA security. Think of it like this. Authentication asks, who are you? And makes you prove it. Authorization then asks, okay, now that you're in, what are you allowed to do? And finally, accounting keeps track of everything, asking, what did you do while you were here? It's all about visibility and control. You know, the best way to think about AAA is to just look at your credit card. The card itself, with your name on it, proves you are who you say you are. That's authentication. Your spending limit, that's your authorization. You can't do more than you're allowed. And that statement you get every month that shows every single purchase, yep, that's accounting. It's the exact same idea just for your network. Next up in our toolkit is a big one, the firewall. Seriously, the best way to picture a firewall is as the bouncer at the front door of a really exclusive nightclub. And that nightclub is your network. It stands right at the entrance, checking every single packet of data trying to get in or out. It's got a strict guest list, a set of rules, and if you're not on the list, you're not getting in. It's your absolute first line of defense. So how does this bouncer decide who gets in? Well, it can do a few things. It can do some basic packet filtering, kind of like checking an IP address like an ID. It can do application filtering, which is like enforcing a dress code, no sketchy apps allowed. Or it can do URL filtering, blocking known bad websites. But the smartest firewalls use something called stateful packet inspection. This is like a bouncer who's paying attention. It knows that you, a trusted person from inside, just stepped out, so when you come back, it lets you in. But it stops the stranger who tries to tailgate you. It understands the conversation, which is incredibly powerful. Okay, we've talked about some big ideas, firewalls, AAA, but all of this, every single bit of it, comes down to one thing: locking down the actual devices on your network. Your laptop, your phone, your servers. This is where security gets really personal. And let's start with the absolute basics, passwords. For years, we've been told to create stuff like you see on the left, P@SSW0RD1. It's complicated and honestly hard to remember. The new thinking, the better thinking, is on the right, a passphrase, something like 4 tasty waffles and a mug of coffee. Here's the key takeaway. Length is way more important than complexity. A long, memorable phrase is 1,000 times harder for a computer to guess than a short, complex password. This one change is a huge upgrade. Finally, here is your essential checklist. We call this device hardening. First, and I can't say this enough, change all default usernames and passwords right away. Second, lock it down. Only give access to people who absolutely need it. Third, turn off stuff you don't need. Every extra service running is another potential door for an attacker. Fourth, update everything, always. Those security patches are there for a reason. And last, but absolutely not least, backups. Keep regular, secure backups, and keep a copy off-site. A good backup is your get-out-of-jail-free card when everything else goes wrong. And that really brings us to the most important point of all. Security isn't a product you can buy off a shelf. You can't just buy a firewall and call it a day. It's a process. It's something you do every single day. It's about being vigilant, it's about planning, it's about taking action. So the real question I want to leave you with is this: are you an active part of that process? Because in the end, the strongest digital fortress in the world is only as strong as the people standing on the walls, defending it.
Hey, welcome. You know, every single time you load a web page or send an email, there's this secret conversation happening behind the scenes that makes it all work. Today, we're going to solve the mystery of that hidden process in this explainer on address resolution.
So think about this for a second. You're on your laptop, you hit print, and boom, a few seconds later, the page comes out of your printer. Seems like magic, right? But how does your computer, in this sea of devices, know exactly how to find that specific printer? This simple question, believe it or not, gets right to the heart of how networks actually function. All right, so to crack this case, the first thing you have to understand is that every device on your network, your phone, your laptop, your smart TV, all of it, doesn't just have one identity, it actually has two. Okay, so what are these two identities? Well, think of the IP address as its name. It's how other devices can find it across the huge world of the internet. And just like a name, it can change if you move to a new network. But the MAC address, that's more like a fingerprint. It's a permanent physical ID that's literally burned into the hardware. It's used for direct device-to-device chat, but only when they're on the same local network. And right there, that's the big problem. A device might know the IP name of the device it wants to talk to, but to actually hand off the data directly, it needs that physical MAC fingerprint. It's like you know someone's name, but you still need their street address to actually deliver a package. So, yeah, the stage is set for a little detective story. Your device has a packet of data, it knows the IP address it's trying to reach, but it has absolutely no idea what the physical MAC address is. So, what's it gonna do? Well, every good mystery needs a detective. And in our story, that detective is the Address Resolution Protocol, or as we all call it, ARP. This is the unsung hero that bridges that gap between the logical IP world and the physical MAC world on pretty much any network using IPv4. So how does our detective, ARP, actually work its magic? Let's follow the clues and see how it cracks the case of the missing MAC address. You know, the process is actually brilliantly simple. It really just boils down to 4 key steps. A device has a question, so it makes a request. It then broadcasts that request out to everybody. The right device sends a reply, and then the original device records that info for later. Simple. And that broadcast step, it's literally like shouting in a crowded room. The source device sends out a message to every single device on the local network. It's not subtle, but man, is it effective. Every device on the network just stops for a millisecond and listens to that shout. Now, even though everybody hears that shout, only one device is going to recognize its own IP address in the message. And that device, and only that device, is the one that raises its hand and replies directly back saying, "Hey, that's me. Here's my MAC address." Okay, but shouting across the room every single time would get pretty old, right? So our detective is smarter than that. To be more efficient, it keeps a little notebook. We call it an ARP table or an ARP cache. This is where it writes down the IP to MAC pairings it discovers. That way, next time, it can just look up the answer instead of having to shout all over again. Alright, so our detective is a pro at solving these local cases. But what happens when the mystery goes international? What happens when the device you want to talk to isn't in the same room, but on the other side of the world? Yeah, this adds a whole new wrinkle, doesn't it? Your computer can't exactly shout loud enough to ask for the MAC address of a server in another country. That broadcast wouldn't even make it past your router. So, now what? Well, it talks to the local post office. For your network, that's your router, also known as the default gateway. See, for any message going to a remote network, the goal isn't to find the final destination's physical address yourself. The goal is just to hand the data off to the one device that knows how to get it there. And here's the really clever part. The ARP process is exactly the same. The only thing that changes is the target. Instead of asking for the MAC address of that final server far away, it just broadcasts a request asking for the MAC address of its own default gateway. Once it has that, it can hand off the packet and let the router take care of the long-distance journey. Now, ARP has been our reliable detective for decades, but let's be honest, all that shouting, all that broadcasting, it can get a little noisy on a busy network. That's why the newer internet protocol, IPv6, uses a much more sophisticated and modern method called neighbor discovery. And you can really see the evolution here. Instead of shouting at everyone in the room, a broadcast, IPv6's neighbor discovery protocol uses what's called a multicast. Think of a multicast as a targeted message sent only to a specific group of devices that are actually interested. It's kind of like whispering to just a few people instead of yelling. It's way more efficient and creates much less chatter on the network. So we've followed the clues from local networks all the way to the global internet. We've looked at the old detective and the new one, but what's the final verdict here? Why is this whole detective story so important anyway? It's really this simple. Without address resolution, nothing works. Period. Not your printer, not your connection to the internet, not your smart TV. This constant silent translation from a logical name to a physical fingerprint is the absolute foundation that allows data to actually move from one machine to another. But like in any good detective story, there's a final twist. This entire system we've just talked about, this elegant process of asking and answering, is built on one simple and potentially very dangerous assumption, that everyone is telling the truth. And this is where things get scary, because ARP doesn't actually verify who's responding,
A bad guy in the network can send a fake reply. They can just lie and say, hey, I'm the router. And your device, which is built to trust these replies, will then send all of its internet traffic, passwords, emails, bank info, everything directly to the attacker. This is called ARP spoofing, and it's a powerful reminder that even our most fundamental protocols can have some serious vulnerabilities. So the next time you connect to a Wi-Fi network, remember that invisible detective, ARP, working tirelessly behind the scenes to connect your device's name to its fingerprint. This hidden conversation is happening constantly, with every single click. And it really makes you wonder, what other invisible protocols, what other secret conversations are running your entire digital life right at this very moment? Have you ever wondered about the secret language that's powering our entire digital world? I mean, every time you hop on Wi-Fi or shoot off an email, your devices are having this super complex conversation that we just never get to see. So today, we're going to dive in and unlock the secret code that makes it all happen. It really all starts with a puzzle. You've probably seen a number just like this one before, right? It's an IP address. It's basically how devices find each other online. But here's the crazy part. At its heart, a computer is an incredibly simple machine. It only gets two things. Electrical current is on or electrical current is off. So how on earth does it get from a simple on or off switch to a number like 192? Well, the answer lies in learning to think like a computer. And that means we have to figure out how to count using only two numbers. This right here is the first key to unlocking that secret language. And that language is called binary. You can just think of 0 as off and 1 as on. It's a base 2 system, and these zeros and ones are the native tongue of pretty much all digital electronics. And this isn't just some clever programming trick. It's a perfect match for the physical reality of a computer's circuits, which are, either on or off. Okay, so before we get totally lost in all these zeros and ones, let's take a quick step back and ground ourselves in the system we use every single day without even thinking twice about it. We use the decimal system, or base 10. And it has this really cool secret that we barely ever notice, something called positional notation. In a number like 1234, that 4 is just 4. But the 3 isn't just 3, it's 30. The 2 is 200, and the 1 is 1000. The position of the number changes its value. And that idea, that's the key. So if we put our two systems side by side, you can really see the pattern. We use base 10 with 10 different digits, where each position is a power of 10. A computer uses base 2 with just 2 digits, where each position is a power of 2. See? It's the exact same idea, just with a different base number. And this is exactly how it works. Instead of a ones, tens, and hundreds column, binary has a ones, twos, fours, eights column, and so on. Each spot is just double the last one. So when a computer sees the binary number 11000000, it's really just reading, okay, I've got 1128 and 164. It adds them together, and what does it get? 192. Hey, that's the first number from our IP address. All right, we found our first key, so now we can actually use it to decode the rest of that mysterious address. Let's put this new binary knowledge to work. But first, just a quick piece of vocabulary. Each of those numbers in an IP address, like the 192 or the 168, it's called an octet. And why? Well, because it's represented by 8 bits, or 8 of those binary zeros and ones. An IP4 address is really just 4 octets all strung together. So how do we convert 168? It's actually like a simple little subtraction game. We just go right down the line of our binary place values. Is 168 greater than or equal to 128? Yeah. So our first bit is a 1, and we subtract 128. That leaves us with 40. Next up, is 40 greater than or equal to 64? Nope. So our next bit is a 0. Is it bigger than 32? Yes, it is. So we put down a 1 and subtract, leaving us with 8. We just keep doing this until we have our full binary number, 10101000. And there you have it. The IP address that we humans read as 192.168.1110 is actually seen by your computer as this long string of 32 ones and zeros. So the really important thing to get here is that this isn't a different number. It's just a different way of writing the exact same number. Mystery solved. Or is it? For the older IPv4 addresses, that system works just fine. But technology moves fast. And the modern internet, well, it needs addresses that are way, way longer. And that's a problem, because binary can get really long and just plain clumsy for us humans to read. A modern IPv6 address isn't 32 bits long. It's a whopping 128 bits long. That is 4 times the amount of information packed into just one address. Can you imagine trying to write that out in pure binary? It would be an absolute nightmare. We desperately need a better way. A kind of shorthand, a new translator. And that translator is hexadecimal. It's a base 16 system. Now to get 16 digits, it uses our normal 0 through 9, and then it just adds the letters A through F to represent the values 10 through 15. Its entire reason for being is to represent those long, clunky binary numbers in a much shorter, more elegant way. Yeah, this quote from the source material really just nails it. The magic of hexadecimal is that one single hex character can stand in for a group of 4 binary bits. It's a super efficient compression system for our eyes. And just to really feel the scale of this problem, this is a real IPv6 address in its full 128-bit binary form. I mean, look at it. It's just a wall of numbers. Try reading that. Try typing it without making a single mistake. It's practically impossible for a person to work with. Now, look at that exact same address translated into hexadecimal. All of a sudden, that impossible wall of numbers becomes clean, it's manageable, it's something a network engineer can actually read and work with. The difference is just staggering, and it's precisely why hexadecimal is so critical for the modern web. So let's take a look at this master key, this translator in action. How exactly does it pull off this magic trick of turning these ridiculously long binary strings into short, readable text? It's actually a beautifully simple 3-step process. Let's go back to our number 168. First, we convert it to its 8-bit binary, which we already figured out is 10101000. Step 2, we just split that into 2 little groups of 4, 1010 and 1000. Finally, we convert each group. So for 1010, that's an 8 plus a 2, right? Which equals 10, and in hex, 10 is just A. The second group, 1000, well that's just an 8. Put them together and you get A8. That's it. That's the translation. So what have we unlocked today? What's the big takeaway? We've seen that binary, base 2, is the true native language of the machine. Decimal, base 10, that's our human language for counting. And hexadecimal, base 16, is that essential translator that bridges the gap between the two, making modern networking even possible. These aren't just abstract math ideas. They are the living, breathing languages of our connected world. And that leaves us with a really fascinating final thought. Binary and hexadecimal were designed for the electrical computers of the 20th century. But as we start moving into totally new eras of computing, like quantum computers or biological systems, what will their secret languages look like? What's going to be the next step in this amazing evolution of code?
Ever wonder what's really going on inside your network? Well, you're in the right place. Today, we're going to walk through step by step how to install one of the most powerful network tools you can get your hands on, Wireshark. Let's jump right in. Think about it. Right now, as you're listening to this, your computer is having a constant secret conversation. It's sending and receiving tons of invisible data, talking to routers, servers, you name it. But what's it saying? What kind of secrets are hiding in that digital chatter? And that is where Wireshark comes into play. It's basically the ultimate network eavesdropping tool. They call it a packet sniffer. What it does is it grabs all those little data packets flying across your network and cracks them open so you can read them. It literally makes the invisible visible. Alright, so before we actually get to installing this thing, let's just cover a couple of quick essentials, just to make sure this whole process is super smooth for you. And the great news is, you really don't need a whole lot. For what we're doing today, all you need is a Windows PC, a decent internet connection so you can grab the download, and, well, a few minutes of your time. That's literally it. Now, this next part is critical. Seriously, listen up. Because Wireshark can see everything happening on a network, you should only ever use it on a network that you personally own. If you're thinking about using this at school or at your job, you have to get permission first. No exceptions. Okay, with that important PSA out of the way, we're good to go. Let's move on to step 1, the download. First things first, we gotta get the software. And you wanna make sure you're getting the real deal, the safe version. So head straight to the official website, wireshark.org. Seriously, don't download it from some random third-party site. Once you're on the download page, you'll see a couple of choices. Look, for pretty much any modern Windows computer, you're going to want the Windows Installer 64-bit. If you happen to be on a Mac or Linux, no worries, just grab the one for your specific OS. Go ahead and click that download button. Alright, file downloaded? Perfect. Now we're ready for the main event. Let's dive into step 2 and actually get this thing installed. This part's super easy, I promise. Just find that file you downloaded, it'll probably be in your Downloads folder, and double-click it. You'll probably get a security pop-up from Windows, just hit yes or allow. Then the setup wizard will launch. Just click through the first screen or two until you get to the license agreement and, you guessed it, click I agree. And here's the best part. For the next few steps, you barely have to think. The default settings are exactly what you want. So when you see choose components, just leave it all checked and hit next. Same for shortcuts, hit next. And for the location, yep, just hit next. Trust me, the defaults are perfect. Okay, so the installer is going to bring up something called NCAP. Now, this isn't just some optional add-on, it's actually the heart of the whole operation. It's the engine that lets Wireshark grab live data right off your network. Without NCAP, Wireshark is kind of useless for live analysis, so yeah, we definitely need to install this. Whoa, stop for a second and pay close attention to this screen. You're going to see an option for something called USB PCAP. I need you to leave this box unchecked. Do not install it. It's an experimental feature and it can seriously mess with your USB ports, so just leave it blank and click install. We are so close. A new little window is going to pop up for NCAP. Just click I agree, then install. Once that's all done, click finish. That little window will disappear and you'll be right back in the main Wireshark installer. All you have to do now is click next and then that beautiful finish button. And that's it. With just a few clicks, you did it. But think about it. You didn't just install some program. You've basically just given yourself a new superpower. Seriously? Congratulations. Installation is complete. You now have a professional-grade, industry-standard tool sitting on your desktop. This is the exact same software that network pros and security experts use every single day. So what does this mean for you? Well, now you can figure out why your Wi-Fi is so slow. You can see exactly what servers your favorite apps are talking to. And best of all, you can finally understand how networks actually work from the ground up. You've got the key. You can now listen in on every single digital conversation happening on your network. So the only real question is, now that you can see everything, what are you going to go discover first?
All right, today we're going to do something really cool. We're bringing a network router to life. We're literally starting with a brand new device, just a metal box, right? And we're going to turn it from a blank slate into the intelligent brain of an entire network. Let's dive in. So, here's the big question. How do you actually teach this thing to do its job? See, when it comes straight out of the box, a router is pretty much useless. It's got all the hardware, but zero instructions, no security, and it has absolutely no idea how to talk to the rest of the world. So our job is to give it that intelligence, one command at a time. And here's our game plan. First, we'll go from box to brain. Then, we'll give it a basic identity and lock it down tight. After that, we'll configure its network connections, set it up as the default gateway, and finally, we'll double check everything to make sure it's all working just right. Okay, first things first. From box to brain. The router's plugged in, the lights are blinking, but it's just sitting there, waiting for us to tell it what to do. Our first mission is to give it those initial instructions to turn it into the network's command center. Next up, we've got to give our router a basic identity and, more importantly, some security. Think of it like a new hire at a company. Before they can get access to anything important, they need a name badge and a password, right? Same idea here. These first steps are absolutely non-negotiable. So this is our foundational checklist. We're going to give the device a unique name, slap some secure passwords on it, post a legal warning for anybody trying to log in, encrypt those passwords so nobody can read them, and then, super important, we're going to save all our work so it doesn't just disappear. And boom, here's our very first command. It looks simple, but it's so important. Hostname R1 just changes that generic name router to R1. Why does that matter? Well, if you have 10 routers on your network, you need to know exactly which one you're logged into. It's all about clarity. Next, enable secret class. This command is all about protecting the most powerful access level on the router, what we call privileged exec mode. This is basically the keys to the kingdom. Using the word secret here is key because it makes sure the password, in this case, class, is heavily encrypted and hidden from view. Now we're securing the router's physical front door. The line console 0 command lets us put a password on the physical port you'd plug a cable into. This is huge because it stops someone from just walking up to the device, plugging in, and taking over. Okay, this next one is a huge deal for security. Without this command, some of those passwords we just set would be stored in plain, readable text inside the configuration file. Not good. This one little command, service password encryption, scrambles them all, adding a massive layer of security. Think of this as putting up a digital keep out sign. The banner mod, or message of the day, flashes this warning to anyone before they even get a chance to type in a password. It's a clear legal heads up that this device is for authorized users only. Alright, this is probably one of the most important commands you'll ever type. See, everything we've done up to this point only exists in the router's temporary memory, the running config. If the power goes out, poof, it's all gone. This command copies our work over to the permanent startup config, making sure our setup is still there after a reboot. It's the save button for your network. Okay, so our router has a name, it's locked down. Now it's time for the main event, teaching it how to actually connect to networks and do its real job, which is routing traffic. This is where it goes from being just a secure box to an active part of the network. To do that, you gotta understand what an interface is. And really, it's simple. It's just a physical port on the router. Think of it as a doorway that leads out to a specific network. And just like a house on a street, every single doorway needs its own unique address, so traffic knows exactly where to go. And here are the 4 basic commands you need to set up one of those doorways. First, you pick the door you want to work on. Then, you give it a label so you know what it's for. Third, you assign it that unique address. And finally, and this one's easy to forget, you type no shutdown to actually open the door and let traffic flow. Let's see it in action. Here, we're giving the interface its IP address and subnet mask. Then, we hit it with the no shutdown command. That's like flipping the on switch. Instantly, that port comes to life. And just like that, a router is officially communicating on its first network. Awesome. Our router is talking to its local buddies. But what happens when your computer wants to reach Google or watch a video on YouTube? It needs a path to the great wide open internet. And that's where the default gateway comes in. So here's the deal. Whenever your computer needs to send something to a network it doesn't recognize, like pretty much the entire internet, it doesn't just give up. Instead, it sends that traffic to its default gateway. And that gateway is our router, which basically acts as the official exit ramp, promising to get that traffic on its way to wherever it needs to go. This slide really breaks it down perfectly. On the left, you've got your local network, all your devices that can chat with each other directly. On the right, you've got, well, everything else. The default gateway is that single interface on our router that acts as the bridge, the one critical link between your private little world and the rest of the internet. Okay, we've done all the work, we think. We gave it a name, secured it, set up its interfaces, but are we really done? Nope, not even close. The final, and I'd say most professional step, is to actually verify that everything we just did is working the way we expect it to. And this quote right here is the golden rule of network administration. You trust that you type the commands in right, but you always verify the results. You never just configure something and walk away assuming it works. Trust me, this simple habit will save you from countless headaches down the road. Our first check is the show IP interface brief command. Now, the 2 columns you really care about here are status and protocol. What we want to see, the money shot, is up and up. The first up means your physical cable is good. The second up means the software side is communicating. That is a perfect bill of health for our connection. Next, let's peek inside the router's brain with show IP route. This command shows us the router's personal map of the network. That line, starting with a C, confirms it knows that the 192.168.10.0 network is directly connected. It successfully learned about its own neighborhood, which is exactly what we want. And this table right here, this is your takeaway toolkit. These are the 3 essential commands you'll use all the time. Show IP interface brief for that quick status check. Show IP route to look at the map. And show interfaces for when you need to see all the nitty-gritty details. If you master these 3, you are well on your way. So, in just a few minutes, look what we've done. We've taken a blank metal box and turned it into a secure, connected, and intelligent network brain. We brought it to life. And that leaves us with one last question to think about.
Now that our router is up and running, what's the very first thing it needs to do? Thanks for watching.
You know, when you unbox a brand new network switch, it's really just a metal box, right? A bunch of ports, some lights. But have you ever wondered how that simple box turns into the intelligent beating heart of a network? Well, today, we're going to pull back that curtain and look at the very first steps of that magical process. And that's really the big question, isn't it? How do we go from this inert piece of hardware to something that's actually the backbone of our network? Well, I'll tell you, it's not magic, it's configuration. We are literally going to give this box a name, a brain, and some basic security. By the end of this, you'll get the absolute most critical first steps to bringing a network to life. Okay, so most of us live in a point-and-click world, right? We're used to a graphical user interface, a GUI. It's all icons and windows, super friendly. But in the world of professional networking, the real power, that's in the command line interface, the CLI. It's all text. You tell the device exactly what to do. Yeah, it might look a little old school, but it is way faster, way more powerful, and this is the key, it's scriptable. You can automate tasks in a way you just can't with a GUI. That's why it's still the gold standard for pros. So how do we even get to that command line? It's not like you can just plug a keyboard and monitor into the switch. Our very first challenge is to actually make contact with this thing and wake it up. Think of it like there are three main doors into a switch. You've got SSH and Telnet for connecting remotely. But here's the catch. They work over a network. Our brand new switch, well, it isn't on the network yet. That's where the console port comes in. It's a special physical port that gives us direct access, kind of like a secret backdoor. For that very first setup, the console port is our key to the front door. All right, we're connected. We are now inside the switch's operating system, which is called Cisco iOS. But you can't just start typing commands wherever you want. The iOS has different levels of access, or what we call modes, and each one has its own set of privileges. You can think of them like different security clearance levels. The first place you land is called user exec mode. I always think of this as the lobby. You can walk around, check some basic stats, see what's going on, but you can't actually change anything. It's a totally safe, read-only space. And take a look at the command prompt. See how it ends with that greater than symbol? That's your clue. Now, to get some real work done, we need to level up our privileges. We do that by typing a simple command, enable. And that takes us into privileged exec mode. If user exec was the lobby, this is the control room. From here, you can do literally everything. Reboot the device, view secret configs, you name it. This is the keys to the kingdom. And the coolest part is, the device itself tells you exactly where you are. You just have to look at the prompt. It changes from that greater than symbol to a hash mark when you go from user to privileged mode. And when we go even deeper to actually make changes, it changes again to config hash. Seriously, that little prompt is your GPS inside the switch's OS. Okay, so we're in the control room, we know how to get around, so what's the very first thing we should do? We've got to give the switch an identity. By default, its name is just switch. Imagine having a dozen devices all named switch. Yeah, not very helpful. And luckily, the process is super straightforward. From that privileged mode, the one with the hash mark, we type configure terminal. That tells the switch we're about to make some system-wide changes. Then we just use the hostname command followed by whatever name we want, like SW1. And bam, look at that. The prompt changes instantly to show the new name. It's a small step, but it's the first official mark we've made on our configuration. Awesome, our switch has a name. Now what's next is absolutely 100% non-negotiable. Security. We have to lock down access to that super powerful privileged exec mode we just learned about. Now before we even type a command, let's just quickly talk about what makes a good password. I'm not talking about password or 12345. A strong password is your first best line of defense. Just think two things, length and complexity. The whole idea is to make it ridiculously hard for anybody or any computer program to guess it. The command we use for this is so important. Enable secret. Now there are older, less secure commands, but this is the one you want. Why? Because when you use enable secret, it doesn't just set the password for privileged mode, it automatically stores it using a really strong encryption method. This is the modern secure way to protect your device's control room. So a password stops people, but a banner warns them first. By using the banner mod command, which stands for message of the day, we can flash a warning message to anyone who tries to connect. From a legal standpoint, this is huge. It makes it crystal clear that this device is for authorized folks only. And those hash symbols you see, they're just bookends. They tell the switch where your message starts and stops. Okay, this is great. We've named our switch, we've secured it, but right now all of our amazing work only exists in the switch's temporary memory. If someone unplugs it or the power goes out, poof, everything we just did is gone forever. We have to make these changes permanent. To get this, you just need to understand two key files. The running config is what the switch is using right this second. It's live, it's active, and it lives in RAM, which is temporary memory. Think of it like an unsaved Word document. Then there's the startup config. That's the saved copy, stored in permanent memory called NVRAM. When the switch boots up, it copies that startup config to become the new running config. So our job is simple. We need to copy our changes from the unsaved document back to the saved file. And this is the command that makes it all happen. Seriously, this might be one of the most important commands you'll ever type. Copy running config startup config. You run this from privileged exec mode, and it does exactly what it says. It takes a snapshot of the live configuration and saves it as the startup file. Now, if that switch reboots, our hostname, our passwords, our banner, it will all still be there. We've done it. We've configured the basics, we've saved our work, and now it's the moment of truth. We need to actually check if our switch is not just configured correctly, but if it can actually talk to other devices on the network. And the perfect tool for this job is ping. It's a simple command, but it is so powerful. Basically, it sends a tiny little data packet out to another device and says, "Hey, can you hear me?" If that other device is online and gets the message, it sends a reply back. It's the most fundamental way to test if you have a connection from point A to point B. And this right here, this is what success looks like. 100% success rate. That means every single hello we sent out got a reply. This one line of text confirms everything for us. It means our basic config is working, the cables are plugged in right, and our switch is officially an active communicating member of the network. We brought it to life. So there you have it. We took a silent, empty box and we gave it a voice. We've laid the absolute essential foundation for a secure, functional network. But this is really just scratching the surface. This is just the beginning. Now that the switch is online and listening, the real question is, what are you going to tell it to do next? Hey everyone, and welcome. Today, we're going to demystify what it really takes to build and manage a small office network. We are pulling back the curtain on all the routers, switches, and secret handshakes that power our digital lives. By the end of this, you'll be thinking like a true digital architect. So, let's dive right in. You know, we plug into Wi-Fi, we browse the web, we do it every single day without a second thought. But have you ever really stopped and wondered about that invisible architecture that's holding it all together? It can seem super complex, but honestly, it's all built on a foundation of some surprisingly simple and logical principles. So, here's our game plan. We'll start with the blueprint, the planning phase. Then we'll learn the language that devices use to talk to each other. After that, we'll see how to check a network's health. Then comes the fun part, playing detective and troubleshooting. And finally, we'll look at how to grow from small to big. These are really the 5 key stages in the life of any network. First up, the network blueprint. Look, you wouldn't build a house by just throwing up walls wherever you feel like it, right? It's the exact same with a network. A solid, well thought out plan is the absolute foundation for something that's not only reliable, but also easy to manage down the road. Now, when you're picking out your hardware, your routers and switches, the real trick is finding the right balance. You're constantly weighing the cost against what you actually need, like port speeds. But you've also got to think about the future. Is this equipment going to grow with you? What kind of cool features does its operating system have? This isn't just a shopping trip, it's a strategic decision. A good rule of thumb, plan for at least 50% growth over the next few years. I love this analogy. An IP addressing scheme is exactly like a city's postal system. Every single device, your computer, your printer, even your smart TV, needs its own unique mailing address. If you plan this out from the very beginning, it makes it so much easier to find devices and fix problems later on. It really just brings order to the chaos. And this is your network safety net. Think of redundancy as having a spare tire in your car. If your main internet connection goes down or a critical switch fails, a duplicate one just kicks in instantly. It's a simple concept, but it's what separates a fragile network from a really resilient one that can handle a few bumps in the road. Okay, so you've got all your shiny new hardware in place, but how do these things actually talk to each other? Well, they need a shared set of rules, right? A common language. And that is where network protocols come into play. This right here is the fundamental toolkit. Think of DNS as the internet's phone book. It turns easy to remember names like google.com into the actual numbers, the IP addresses. Then you've got DHCP, which is like a friendly assistant that just automatically hands out those IP addresses to new devices. HTTP is the language your browser speaks to websites, and SMTP and POP3, that's the digital postal service for all your email. Of course, you don't want to be shouting your secrets across a crowded room, and that's why we have secure versions of these protocols. Using things like HTTPS or Secure Shell, SSH, is like putting your important data inside an armored truck instead of just sending it on a postcard. It's absolutely crucial for security. All right, your network is officially up and running. That is fantastic. But how do you know if it's actually healthy? Just like a doctor checks your pulse, a network admin needs tools to check the network's vital signs. And the most basic fundamental health check is a little command called ping. This analogy is just perfect. Your computer sends out a tiny signal, a Marco, to another device. If it gets a reply back, a polo, you know there's a connection. It is the fastest way to see if something is even there. But what happens if your Marco gets nothing but silence in return? You need to know where the signal got lost, and that's where a tool called traceroute comes in. While ping just asks, are you there? Traceroute asks, how do I get there? It literally maps out every single stop your data makes along the way, showing you exactly where the connection is breaking down. So let's be realistic for a second. Things are gonna go wrong. It's just a fact of life. Cables get unplugged, software gets buggy, but troubleshooting isn't about panicking. It's about putting on your detective hat and following a methodical process to find the culprit. And you know, professional detectives don't just wing it. They follow a script. And this 6-step process is the heart of effective troubleshooting. You start by clearly identifying the real problem. You come up with a theory about what might be wrong. You test that theory. And then, and only then, do you actually try to fix it. Afterwards, you make sure it worked. And this is so important. You document everything for the next time it happens. All right, let's look at a classic mystery. A user reboots their computer and bam, suddenly they can't connect to anything. No internet, no network files, nothing. So, what's our very first clue? Well, we go check their IP address. And we find this. If you ever see an IP address that starts with 169.254, that is a massive clue. It's called an IPPA address. It basically means the computer tried to find that automatic address giver, the DHCP server we talked about, and couldn't. So it just gave itself a temporary, I'm on an island address. This tells us the problem isn't the internet itself, the problem is somewhere on our local network. Okay, on to our final section. Let's say your small network is humming along perfectly. But what happens when your business starts to take off? A network that was built for 10 people just isn't going to work for 100, not without a smart plan for expansion. So, scaling up without pulling your hair out really comes down to these 4 things. You need your original blueprint, your documentation. You need to know exactly what devices you have. You need a budget, of course. And maybe most importantly, you need to analyze your traffic to see who and what is using up all the bandwidth. That data tells you everything you need to know for upgrades. For example, if you see your main router is constantly hitting over 75% usage during the day, that's a blinking red light telling you to start planning an upgrade before things get slow for everyone. So after all this, what's the big takeaway? Well, it doesn't matter if it's a tiny office with 5 people or some massive global company. The core principles are exactly the same. You need solid planning, a common language of protocols, and a methodical way to solve problems. The entire internet is really just a network of networks, all built on these same ideas. And that brings us to the end. You've seen the blueprint for a digital lifeline. And as you can see, it's not magic. It's just logic, good planning, and a little bit of detective work. So the question I'll leave you with is this. Now that you know the blueprint, if you were starting from scratch, what would be the very first digital brick you'd lay? Thanks so much for joining me. All right, let's jump right in. Today, we're decoding the internet's address book. We're going to figure out what those numbers you see everywhere actually mean and how they work like a global GPS, guiding every single thing you do online right to its destination. So, you've definitely seen an address like this, right? Maybe when you were messing with your Wi-Fi settings. It looks like a totally random jumble of numbers, but I promise you, it's a super precise location on the internet's map. And in the next few minutes, we're going to learn exactly how to read that map. Okay, so the easiest way to wrap your head around this is to imagine the entire internet as one giant global postal system. Every email you send, every video you watch, every website you visit, think of them as packages. And for a package to get delivered, what does it need? An address. That's exactly what an IP address is, a unique mailing address for every single device connected to the internet. All right, let's break this thing down. It's not just one long random number. Nope. Just like your home address has a street in a city, an IP address has two very distinct parts that work together to pinpoint a location. So part one is the network portion. That's basically the zip code. It gets your data packet to the right general neighborhood online. Part two is the host portion. That's the specific street address. It tells the network, okay, once you're in this neighborhood, deliver the package to this exact house, or in this case, this exact device. Okay, but wait a minute. If it's all just a string of numbers, how in the world does a router or a computer know where that zip code part ends and the street address part begins, right? It needs some kind of special decoder ring to figure it out. And that decoder ring is called a subnet mask. It's another set of numbers that pairs up perfectly with the IP address. Its one and only job is to draw a clear line in the sand separating the network part from the host part. So how does this decoder actually do its thing? Well, it's surprisingly simple. You'll see. Let's take a look at how applying this mask can instantly reveal a network's true identity from just a simple string of numbers. All right, here's our sample IP address. As it is right now, we have no idea which part is the network and which part is the specific device. It's basically a coded message that we need to decipher. And now for the magic trick. We apply its subnet mask. The rule here is super simple. Wherever you see a 255 in the mask, the number right above it is part of the network. And wherever you see a 0, the number above it is part of the host or the specific device. That's it. And boom, just like that, the network's identity is revealed. The mask tells us, hey, keep the parts that line up with the 255s, the 172, and the 16, and just ignore the rest. So we now know that the device 172.16.4.1 lives on the 172.16.0.0 network. We've found our zip code. Now, if you want to get technical about it, the official term for this whole process is called ANDing. It's a binary logic thing. But honestly, you don't need to be a computer scientist to get this. Just picturing those numbers lining up is really all you need to understand the concept. Okay, so now we know how to identify a network. But what if that network is absolutely massive, like for a big company with thousands of computers? Having all those devices shouting in the same digital room at once would be total chaos. You've got to divide it up. And the absolute best way to think about that is by slicing a pizza. So why bother? Why would you want to create all these little mini networks or subnets? Well, just like a pizza, slicing it up makes the whole thing a lot more organized, manageable, and efficient for everyone. Yeah, slicing a big network into smaller subnets has some huge perks. For performance, it seriously cuts down on digital traffic jams. It also contains broadcast traffic, which means one chatty device can't slow everyone else down. And for organization and security, it's a game changer. You can group devices however you want, like putting all the accounting department's computers on their own secure subnet, totally walled off from everyone else. Now this is where it gets really interesting. This slide shows the fundamental trade-off of subnetting. It's kind of like a seesaw. The more subnets you create, so the more slices you cut into your pizza, the smaller each individual slice gets. Just look at the chart. As the number of subnets goes up, the number of devices you can have in each one goes down. It's a balancing act. All right, let's bring all of this back home. How does this connect to that 192.168.1.1 address we saw at the very beginning? Because that address belongs to a very special, very common kind of network, your own private one at home. See, on the internet, there are two main flavors of addresses. You've got public IPs, think of that as the main street address of an apartment building. It's totally unique and the whole world can see it. And then you have private IPs, like the one we started with. These are like the apartment numbers inside the building. they're not visible from the outside, and every single building in the world can reuse the same numbers. Apartment 101, apartment 202, and so on. Which leads to a pretty big question, right? If your phone and your laptop all have these private internal apartment numbers, how on earth do they get any mail, any data, from the public internet? There's got to be someone at the front door managing all the mail. And that's where the magic happens. It's a process called network address translation, or NAT for short. The absolute perfect analogy for NAT is to think of your router as the doorman for your apartment building. It's the only one with a public street address, and its job is to manage every piece of mail coming in and going out for every private apartment inside. And this slide shows you exactly how that doorman works. It's like a quick 5-step dance. First, your laptop, with its private address, wants to go to a website. The router, our doorman, grabs that request. It cleverly swaps out your private address for its own public address and sends it off. When the website responds, it sends the data back to the doorman's public address. The router then checks its logbook, sees, the laptop in apartment 3B asked for this, and delivers the data right back to you. It's brilliant. And that brings us full circle. That address, 192.168.1.1, is simply the common default private address for the router itself. It's the internal office number of our doorman, the device standing at the gate between your cozy private network and the huge public internet. Mystery solved. Look at this number. Almost 4.3 billion. That is the total number of addresses available in the original IPv4 system. Back in the 1980s, that must have seemed like an infinite amount. But today, well, it leads us to one last, really crucial question. Think about it. Today, there are tens of billions of devices online. So how have we not run out of addresses? Well, the answer is that clever doorman, NAT, working with all those private addresses. It's an ingenious system that has let us stretch IPv4 way beyond its original limits. But what happens when even that's not enough? Well, that is a story for another explainer.
You know, every single device you own, your phone, your laptop, even your smart TV, it has a secret identity. It's this unique, unchangeable fingerprint that lets it talk to the rest of the world. Today, we're going to pull back the curtain on that digital passport. We're talking about the MAC address. So let's just start with a scenario you've definitely been in. Picture it. You're at a busy coffee shop. Everyone's on the same Wi-Fi network. You click on a video, and somehow it streams perfectly to your screen, not the person's next to you. How in the world does the router know who's who? It feels like magic, but it's not. It's technology, and we're about to unravel it.
Well, the secret is that your device is actually juggling two different addresses at the same time. You've probably heard of the IP address, right? Think of that like your hotel room number. It's temporary and it just tells the network where your device is right now. But the MAC address, now that's the important one. That's your device's permanent fingerprint. It doesn't say where it is, it proves who it is. And that makes all the difference. Okay, let's get just a little bit technical for a second. The official name is Media Access Control Address. It's a 48-bit identifier that's literally burned into your device's network hardware right at the factory. That's why you'll often hear it called the physical address or hardware address, because it's tied to that physical piece of equipment for life. So, what does this digital fingerprint actually look like? Come on, let's break one down and see what kind of secrets it's hiding inside. Here is a totally real MAC address from an actual device. It's just a series of 6 pairs of letters and numbers. Now, at first glance, it just looks like a random jumble, right? But believe me, there is a very, very specific structure going on here. See, we can actually split this thing right down the middle. It isn't just one long code, it's made of 2 totally separate parts, and each one tells us a different piece of the story. The first half is something called the Organizationally Unique Identifier, or OUI for short, and this is where it gets really cool. This part is not random at all. It's a special code assigned by the I3EE that points directly to the company that made the device. Get this, if we look up the OUI from our example, that 5C-26-OA, we find out it's officially registered to Dell. So boom, just by looking at the first 3 parts of the address, we know without a doubt that this network card was made by Dell. So if the first half is the manufacturer, the second half is the unique serial number that Dell assigned to this one specific card. It's that combination, the maker's ID plus the device's own serial number, that guarantees no 2 devices in the world should ever have the exact same MAC address. Pretty clever, right? Okay, so this secret ID is on all your stuff, but where is it hiding? Let me show you how you can actually go and find this address on your own computer right now. So, if you're on a Windows PC, you can pop open a command prompt and type in ipconfig/all. You'll get a whole bunch of text, but scroll through and look for a line that says physical address, and there it is. Our example, 5C-26-OA-24-28-60. See? Even your computer knows it's the physical address, tied right to the hardware. Alright, so we get it on a single device, but let's zoom out a little. How do the pieces of network gear, like a switch, use this information to manage the traffic for that whole coffee shop we were talking about? The best way to think about a network switch is like a super efficient traffic cop at a really busy intersection. Its whole job is to make sure every piece of data gets exactly where it's supposed to go, fast and without causing a traffic jam. And to do that, it needs to know who's who. So here's what it does. The switch builds a little map or a table inside its memory. And this map keeps track of which temporary IP address belongs to which permanent MAC address. This little map is absolutely crucial for any local network to function properly. And here, we're actually taking a peek inside the brain of a switch. This is its ARP table. That stands for Address Resolution Protocol. And this table is that map. You can see it, plain as day. On the left, there's an IP address, 192.168.1.3, and right next to it, the hardware address, our MAC address. The switch knows exactly who is who. But wait, it actually gets one level deeper than that. The switch doesn't just know who the device is, it also knows exactly where it is physically plugged in. So check this out. This is a different table, the MAC address table. And look, the switch has learned that the device with our MAC address is plugged into its port named FA0/6. So when a piece of data arrives for that device, the switch doesn't have to guess or shout. It just says, I know you. You're on port 6. And sends the data only down that one specific cable. It's ridiculously efficient. So we've seen what it is, where to find it, and how networks use it. But let's get to the big question. Why does any of this actually matter in the real world? Well, it turns out this little address plays some pretty huge roles. For starters, security. You can actually set up your network to only allow a specific list of MAC addresses to connect. It's like having a VIP list at the door of your Wi-Fi. It's also critical for troubleshooting. If one device is causing chaos, the MAC address helps you find that exact machine. Remember the OUI? That helps you identify what kind of device it is, a laptop, a phone, whatever. And most importantly, it's the fundamental language all your local devices use to talk to each other. Okay, but wait a second. This brings up a really good question. What if your computer wants to talk to another computer for the very first time? It knows the IP address, sure, but it doesn't know that all-important MAC address yet. So, how does it find it? It basically shouts, no, seriously? The device sends out a special message called an ARP request to everyone on the network. It's the digital version of yelling across a crowded room. Hey, who here has the IP address 192.168.1.3? I need to know your MAC address. And then, the one device with that IP politely raises its hand and replies with its permanent hardware address. And that shout? It has a very special destination address. All Fs. FF, 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 FF. This is the universal broadcast address. When any network gear sees a message sent to this address, it knows the rule. Send this out on every single port to every single connected device. It is the ultimate "is anyone out there" signal. And that brings us to our final thought for the day. We've established that every single one of your network devices has a permanent, unique fingerprint burned into it at the factory. And we've just seen that in order to communicate, it sometimes has to shout this identity out for everyone nearby to hear. So, if you have a permanent, broadcastable fingerprint, what does that really mean for your privacy in a world that's more connected every single day? Something to think about. You know that little blinking box in the corner of your office? The one with all the cables plugged into it? Well, today we're going to demystify that thing. It's called an Ethernet switch. And it's basically the silent workhorse that makes your entire local network, well, work. I mean, really think about it. You hit print, and somehow that file zips across the office, bypasses everyone else's computer, and lands perfectly at the right printer. How does it know where to go? It's not magic, but it is pretty brilliant. Let's break it down. The easiest way to picture your office network is like a really busy room full of people. If everyone just yelled out their messages, it would be total chaos, right? Nobody would get anything done. So what you need is a system, a way to pass a quiet note directly to the person you want to talk to without anyone else even knowing. And that's exactly what our devices do. Every single piece of information, whether it's an email or that document you're printing, gets neatly packaged up inside what you can think of as a digital envelope. This makes sure it's addressed to the right place and gets there in one piece. So what is this digital envelope really? I mean, what does it look like? Well, in the networking world, it's got a very specific name and a very specific structure that is the key to this whole operation. It's called an Ethernet frame. This is the official, standardized package for any data moving around a local network. Think of it like this. It's the required, company-issued envelope that everybody in the office has to use to send messages. No exceptions. And if you look at what's on this envelope, it's just so logical. Just like a real letter, it's got a to field, that's the destination address. It's got a from field, the source address. Then of course you have the data itself, which is the actual letter inside. And my favorite part, this little thing called an error check. It's kind of like a wax seal that proves the envelope hasn't been opened or damaged on its journey. Okay, but for this whole to and from system to work, every single device, your computer, the printer, your phone, needs a unique, unchangeable name. A name it was given at birth and that it will have for its entire life. And that name is the MAC address. It's this long 48-bit number, which just means it's usually written out as 12 letters and numbers. And here's the crucial part. It is physically burned into the device's network hardware by the manufacturer. It's permanent. It is, for all intents and purposes, your device's unique serial number. Now this is where a lot of people get tripped up, so let's make this super clear. The MAC address is who you are. It's your permanent name. An IP address, on the other hand, is just where you are right now. The analogy is perfect. Your name never changes, but you might sit at a different desk in the office every day. Your MAC address is your name. The IP address is just your temporary desk number. Alright, so we've got devices with permanent names, and they're sending messages in these perfectly addressed envelopes. So what's missing? We need the mail clerk. We need someone to actually sort and deliver all this mail. And that's where our hero, the Ethernet switch, finally enters the picture. You see, the switch has one incredibly important job. It looks at the destination address on every single envelope that comes through, and it forwards that envelope only to the specific physical port that leads to the right device. It sends the note directly to the right desk. No shouting, no bothering anyone else. Just quiet, efficient delivery. But wait a minute, how does the switch know where everyone is sitting? Is there like a preloaded map of the office? Nope. And this is the magic right here. It does something way smarter. It learns on the job. When you first power on a brand new switch, it is completely clueless. It knows absolutely nothing. Its internal directory, which is called the MAC address table, is totally blank. It's like a mail clerk on their very first day holding a clipboard with no names and no desk numbers on it. So how does it learn? It follows a simple two-step process for every single message it sees. First, it learns. When a message comes in, it looks at the from address and makes a note of which port it came from. So if a frame from PCA comes in on port 1, the switch thinks, got it, PCA is at port 1. Then, and only then, does it worry about step 2, forwarding the message. And you can see that learning process happen right here. After that very first message from PCA, the switch's directory isn't empty anymore. It's got its first entry. Our mail clerk just learned where one person sits and wrote it down on the clipboard. But what about forwarding that message? The switch looks at the to address, which is for printer B. It checks its little directory and nothing. It has no idea where printer B is. So it does the only thing it can do. It sends a copy out to every single port, basically shouting, hey, is anyone out there printer B? It's a one-time broadcast to find someone. Naturally, printer B, which is plugged into port 4, gets the message and sends a reply. And the second that reply hits the switch, what happens? The switch goes right back to its first step. It learns. It looks at the from address on that reply and thinks, aha, so that's where printer B is. Port 4. Got it. And there you have it. The directory gets smarter. Now the switch knows where both devices are. The very next time PCA wants to print something, the switch won't have to shout. It'll just look at its list, see that printer B is on port 4, and send the message directly there. Quiet, efficient, smart. And here's a cool little detail. Switches can act like two different kinds of mail clerks. You got the store and forward type, who carefully reads the whole letter and checks for errors before delivering it. It's slower, but super reliable. Then you have the cut-through type, who just glances at the to address and immediately sends it on its way. It's way faster, but you might end up passing along a corrupted message. Different tools for different jobs. But if there's one thing you remember from all of this, let it be this simple idea.
which Cisco sums up perfectly. The switch dynamically builds its table just by looking at the from address of the messages it sees. That's the secret sauce. It's not programmed, it's a constant learner, building its own map of the network just by paying attention. So there you go. That little blinking box is the intelligent, self-learning brain of your local network. It's the reason everything feels so seamless and fast, all because it's so incredibly good at sorting those digital envelopes. But that leaves us with one last big question. We now know how mail gets delivered inside our own building, but what happens when your computer needs to send a message to a totally different building on the other side of the planet? For that, you need a completely different kind of mail system. And that, my friends, is a story for another time. Let's think about the internet for a second. Imagine it's like a giant global postal service. Every single thing connected to it, your phone, your laptop, your smart TV, needs its own unique address to send and receive information. But what happens if that postal service starts running out of addresses? Well, it basically has. And right now, there's this massive, almost invisible upgrade happening to fix it. Today, we're diving into the internet's next chapter, IPv6. So let's just start with a big question. We have billions upon billions of devices online. Phones, computers, watches, even refrigerators. What would actually happen if we just ran out of addresses for all of them?
And here's the crazy part. That's not some far off what-if scenario. For all practical purposes, we've already hit that wall. The old system, the one the internet was built on, is tapped out.
So yeah, that brings us to the heart of the problem, what we call the internet's address crisis. To really get why the solution is so important, we've got to understand how we ended up in this mess in the first place.
See, the system we've been using for decades is called Internet Protocol version 4, or IPv4 for short. It had a hard limit of about 4.3 billion unique addresses. Now, back when it was created in the 70s and 80s, that number felt astronomical, more than anyone could ever possibly need, right?
Well, you know what happened next. The internet just exploded. First, billions of new people came online from all over the world. Then we moved from dialing up for a few minutes to having our phones and laptops connected 24/7. And now you've got the whole Internet of Things, where everything from your front door to your coffee maker wants its own address. That 4.3 billion didn't stand a chance.
So, with the old system completely full, we obviously needed something new. The good news is the internet's architects saw this coming from a mile away and have been working on the solution for decades. So it's time to meet the successor, IPv6. So what is IPv6? It's the next generation, designed from the ground up to solve this exact problem. The main thing to know is that it takes the address space from 32-bit, which gave us the 4.3 billion, and blows it up to 128-bit. And that doesn't just give us a few more addresses, it gives us an almost comically large number of them. But just how vast are we talking? The number is 340 undecillion. I mean, I don't really know what that number means, other than it's insane. It's enough to give trillions of addresses to every single person on Earth and not even notice. The whole point was to create a system so big, we would never, ever have to worry about this again. Of course, you can't just flip a switch and change the entire internet overnight. So the transition is this really gradual process that uses some pretty clever tricks. Dual stack just means your phone or computer can speak both languages, IPv4 and IPv6. Tunneling is kind of like putting an IPv6 letter inside an IPv4 envelope so it can travel through an old part of the network, and translation acts like a helpful interpreter, letting new and old devices talk to each other. All right, we get it, it's big. But what do these new addresses actually look like? They seem a little complicated. Let's break down the anatomy of an IPv6 address. Yeah, at first glance, they can look pretty intimidating. The standard format is 8 groups of 4 characters separated by colons. And these aren't just numbers, they're hexadecimal, which just means they can be any number from 0 to 9 and also any letter from A to F. So here's what a full, uncompressed one looks like. It's long, it's clunky, and nobody wants to type that out, right? Thankfully, IPv6 was designed with some really simple rules to make them way shorter. Okay, the first trick is super simple. Inside any of these groups, you can just drop any zeros at the beginning. So 0db8 becomes just db8. A whole block of 0000 becomes a single zero. See? It's already looking a lot cleaner. Now for the second rule, which is even more powerful, if you have a string of groups that are all zeros, you can replace that entire section with a double colon. So that 000 in the middle just vanishes and becomes colon. Now the key here is you can only do this once in an address so the computer knows how many zeros to put back. But you don't need to memorize this. The point is just that this scary looking address has simple built-in shortcuts. So we know what these addresses look like, but how does your phone or laptop actually get one when you, say, connects to your home Wi-Fi? Well, the process is actually a lot smarter and more streamlined than it used to be. One of the coolest things about IPv6 is that your device usually gets two main addresses. The first one is its public global address. Think of that as your home's mailing address. It's totally unique and lets you talk to the rest of the world. But it also gets a private local address that it only uses to talk to other things on your home network, like your printer. That's kind of like telling your coworker you're at the desk next to them. It's a perfectly good address, but it only makes sense inside your office. And one of the most elegant things here is how devices can just configure themselves. It's like a little conversation. Your device connects and basically shouts, "Hey, is there a router here?" The router responds, "Yep, I'm here. Here's the info about our network." And then your device just uses that info to create its own address, and boom, it's online. This is huge for the Internet of Things, because you don't want to have to manually configure your smart toaster, right? It just needs to work. This is how that happens. Okay, let's wrap this up by looking at the bigger picture. This massive address space isn't just about connecting more gadgets, it's about fundamentally changing how we organize our networks and what that makes possible for the future. Back in the old IPv4 world, carving up your network into smaller organized pieces, what we call subnetting, could be a real headache. It was complicated and easy to mess up. IPv6 was built with this in mind from day one. The address itself has a specific part baked right into it that's dedicated to identifying these subnets. And the scale, once again, is just wild. A typical standard address block that an ISP might give your home or a small business allows for over 65,000 individual subnets to work with. That kind of built-in organization is exactly what you need to build something like a smart city, where every traffic light and every public bus can have its own logical place on the network. You just couldn't do that sanely with IPv4. All right, let's boil all of that down. What are the big takeaways? 1. The internet's old address book, IPv4, is full. 2. The new one, IPv6, has a practically infinite supply of addresses. 3. Those super long, intimidating addresses have simple rules to make them shorter. And 4. Devices can now get online and set themselves up automatically, which is a real game changer. And all of this leads to one final thought. We know IPv6 is technically better, it's more efficient, and it's absolutely necessary for the internet to keep growing. It is the future. So the big question we're left with is, if it's so great, what's holding back its full universal adoption right now?
Alright, so you've just unboxed a brand new, powerful network switch. It's this sleek piece of hardware, the future backbone of your network, but there's just one little problem. How do you even start talking to it? Well, let's solve this puzzle together and learn the one foundational skill every single network pro has to master, making first contact. And that's the million-dollar question, isn't it? This thing has no IP address. It has no network identity. You can't ping it. You can't SSH into it. For all intents and purposes, it's a digital island. So how on earth do we build that very first bridge to get it online? This is what we call the silent switch problem. Fresh out of the box, a switch is a complete blank slate. Think of it like a powerful engine with absolutely no steering wheel, just sitting there waiting for its very first instructions. Yeah, this really gets to the heart of the issue. You've got all this potential, all these ports, all this processing power, and it's totally locked away until we can establish that initial direct line of communication. We've got to find a way in before the network even exists. And that brings us to the solution, the console port. You can think of this as the backstage door, the engineer's private entrance. It's a special port designed for exactly this situation. It's our way of having a direct physical handshake with the hardware itself. So what exactly is a console port? It's a dedicated interface that gives you direct command line access. And here's the crucial part. It completely bypasses the regular data network. This is our entry point, our secret weapon for initial setup and, for emergencies. Okay, let's actually walk through the physical setup. It's a really simple 4-step process. You're gonna need this special rollover console cable. One end, the one that looks kind of like a network plug, goes right into the switch's console port. The other end, this old school 9-pin connector called a DB9, goes into your computer. Now, let's be real, most modern PCs don't have these serial ports anymore, so you'll almost certainly be using a simple USB to serial adapter. Then you just power everything on. So the physical connection is done, but now we need the software side of things. We have to teach our computer how to understand the raw data that's coming from that serial port. And to do that, we're going to need a special piece of software. In this case, we'll use a program called TerraTerm. TerraTerm is what's known as a terminal emulator. It's basically a window into the switch's operating system. It takes all that serial data and translates it into the text-based command line interface, the CLI, that we can actually interact with. Now, this part is absolutely crucial. For this to work, our computer and the switch have to speak the exact same language. They have to agree on some very specific rules, which you can see here. Think of the baud rate, 9600, as the speed of talking. Both sides have to be set to the same speed. The rest of these settings, they're like the grammar. If any one of these is wrong, the connection fails, and all you'll see on your screen is a bunch of garbled, meaningless text. So after you get your settings configured correctly in TerraTerm and you hit connect, you press enter a few times, and then you see this. This simple prompt, switch, that's the moment of success. That means you've made contact. You're in. Now that we have a connection, we can finally start our first conversation with the switch's brain, its operating system, which Cisco calls iOS. So let's go ahead and issue our first couple of commands. A great first command is show version. This is kind of like asking the switch to introduce itself. It'll tell you everything about its software, its hardware, and how long it's been running. And as we can see here, it's a Cisco 2960 switch running iOS version 15. Next, let's check the time with show clock. And hang on a minute, look at that date, 1993? Yeah, the clock is pretty much always wrong on a brand new device. Now, why does this matter? Well, because accurate time is absolutely essential for troubleshooting. Your log files are useless if all the timestamps are 20 years out of date. So let's fix it. First, we're going to type enable to enter what's called privileged mode. Think of it like getting admin rights. We need it to make any changes to the system. Then we use the clock set command. And here's a pro tip. You can use a question mark at any point and iOS will show you the correct format. Super helpful. Finally, we verify our change. And there we have it. We run show clock again, and the time is now correct. It's a small but really vital first step in setting up a new device the right way. So, we've successfully connected, we set the clock, but why is this fundamental skill so darn important? Let's zoom out from our little lab here and look at the real-world implications. And it's worth a quick mention that while the serial port we used is the classic, the standard for most switches, some newer devices actually use a mini USB console port instead. The principle is exactly the same though. It's still a direct out-of-band connection. Okay, let's bring it all together. Why is this one skill so essential? Because console access is your lifeline. It's not just for the initial setup. More importantly, it's what we call out-of-band management. That means when the entire network is down, when you can't ping, you can't SSH, when everything is on fire, this direct connection will always work. It is the ultimate engineer's fallback, the one tool that can save a device from a total meltdown. Mastering this direct physical connection, this first contact, it's the starting point for every single secure, high-performing network on the planet. From this simple connection, you can build anything. So the real question is, now that you know how to make first contact, what are you going to build? Have you ever really thought about how a tiny piece of your data, a single digital packet, manages to find its way from your computer to, say, a server halfway across the planet, and then back again? All in the blink of an eye? Well, today, we're putting on our detective hats because we're going to solve that exact mystery. Let's get into it. Just think about it for a second. When you type google.com and smack that enter key, your computer is just one little device floating in a massive sea of billions of others. So how on earth does it know the exact path to take? Well, it's not magic, but it is a brilliant system of digital address labels, kind of like a super efficient global post office. Now, to crack this case, every good detective needs their toolkit. We're about to peek into the completely invisible world of network traffic and find the digital fingerprints our computer leaves behind with every single click. Okay, so our number one tool for this investigation is a piece of software called Wireshark. You can think of it as our digital magnifying glass. It's what's known as a packet sniffer, which just means it lets us capture and inspect every single piece of data that comes into or goes out of our computer. This is how we're going to find all our evidence. Every investigation worth its salt starts at home, right? Before we can figure out where our data is going, we first need to know where it's starting from. So our first step is to identify our own computer's digital fingerprints. And we do this with a really simple command, ipconfig/all. Running that command spits out our computer's digital ID card, and it shows us 3 really key pieces of information. First up, our IPv4 address. Think of that as our current street address on our local network. Second, the MAC address. This one is a permanent hardware address that's literally burned into the network card. And third, we have something called the default gateway. Now keep that one in the back of your mind. It's a key suspect in our little mystery. All right, for our first case, we're going to start small. We're just going to watch a conversation that happens entirely inside our own local network. This is going to give us a baseline for the investigation. So the mission couldn't be simpler. We're going to send a ping, which is basically just a tiny, hey, are you there message to another computer that's on the same network as us. And while we do that, we'll have Wireshark capture the whole conversation to see what's really going on. And here it is, our first evidence log. And as you can see, it makes perfect sense. The source IP and MAC addresses, they're ours. The destination IP and MAC addresses, they belong directly to the other computer. It's a simple, straightforward, one-to-one chat. So for local traffic, it's a direct line. Our computer just looks up the other machine's hardware address and sends the data right to it. Easy peasy, case closed. But what happens when the destination isn't just in the next room? What happens when it's on the other side of the planet? And that brings us to our second case, the remote ping. This is where the real mystery kicks in. Instead of just talking to our neighbor, we're now going to send a message all the way across the world, out into the wild west of the internet. Okay, so here's the plan this time. We're going to ping 3 totally different remote servers, Google, Yahoo, and Cisco. You know, they're in different cities, run by different companies, they have completely different IP addresses. And of course, we're going to capture all of it with Wireshark and see what the evidence tells us. All right, the evidence from our remote pings is in, and this is where our case just gets weird. The destination IP addresses are all different, which, is exactly what we expected. But look at the destination MAC addresses. They are all identical, exactly the same. How is that even possible? So that is our big question. How in the world can 3 different servers in 3 different locations all have the exact same physical hardware address? And maybe more importantly, whose address is your case? To solve this mystery, we have to understand that one crucial piece of evidence, those identical MAC addresses. And the answer lies in the fundamental difference between what an IP address is and what a MAC address is. This breaks it down perfectly. Think of an IP address like the street address of a big apartment building. It gets the mail to the right building, somewhere out in the world. The MAC address, though, that's like the specific apartment number inside that building. It's a permanent physical address that only works for finding a device that's in the same building as you. And this right here, this is why our mystery exists in the first place. Your computer, sitting there in its own building, your local network, has absolutely no way of knowing the apartment number or MAC address of a Google server in a totally different building over in California. It only knows the MAC addresses of its local neighbors. So this leads us to the final, really logical question. If your computer wants to send a letter to Google but has no clue what its specific apartment number is, where does it send the packet? It can't just throw it out the window and hope for the best, right? It sends it to the default gateway. This is the single designated front door for your entire local network. Think of it like the building's mailroom. Its one and only job is to take any packet that's meant for the outside world and forward it on its journey across the internet. And that, my friends, is the solution to our mystery. That identical MAC address we saw for Google and Yahoo and Cisco, it wasn't their address at all. It was the physical hardware address of your router, your default gateway. Okay, so let's put all the puzzle pieces together and see how this amazing system lets your computer talk to the entire world without needing to know a single thing about it. So here are the simple rules of the road. For any local traffic, your computer just delivers the packet directly using the other device's MAC address. But, and this is the key, for any remote traffic heading out to the internet, your computer addresses it to the final IP address destination, but it physically hands the packet to the MAC address of its default gateway. From there, your router takes over and forwards it along. It's really that simple. And just like that, the case of the curious packet is closed. It is a beautifully simple and incredibly scalable system. Your computer doesn't need a map of the entire internet. It only needs to know one thing: the address of its own front door, the router. You know, this simple handoff from your computer to your router is happening billions of times every single second, all over the world. It's the invisible heartbeat of the internet. So the next time you're online, just think about it. What other invisible conversations is your network having right now? Thanks for joining our investigation.
Welcome, everyone. Today, we're going to be digital detectives. Yep, we're diving deep into the invisible world of your home network to solve a seemingly simple case: what actually happens when you send a single piece of data. Let's get this investigation started. So here's our central mystery. You type ping into a command line, you hit enter, and boom, you get a reply almost instantly. But that simple little command, it kicks off this incredibly fast, super complex conversation between your computer and your router. Our job today is to expose that secret conversation. And, you know, every good detective needs a tool. Ours is a fantastic one called Wireshark. Just think of it like a digital magnifying glass that lets us see every single message zipping back and forth across our network. It makes the invisible totally visible, and it's exactly how we're going to crack this case. Okay, so before we start intercepting messages, we really need to understand what they look like. See, in the digital world, data doesn't just float around. Nope, it's all carefully packaged up inside something called an Ethernet frame. The easiest way to think of it? It's basically a digital envelope. Let's take a peek inside this digital envelope. You can see it has a bunch of different fields, but for our investigation, two of them are absolutely critical: the destination address and the source address. Just like a real envelope, they tell us exactly where the message is going and who sent it. These right here are our first big clues. And those addresses, they have a special name: MAC addresses. Every single device on your network, your phone, your laptop, your smart TV, your router, each one has a unique MAC address. The best analogy really is a house number. It's a physical address that's only useful for finding a house on one specific street, or, in our case, finding a device on your local home network. So this brings us to the very first problem our little computer detective has to solve. Your PC knows the logical IP address it wants to send the ping to, but it doesn't know the physical MAC address it needs to write on that digital envelope. It literally needs to ask for directions. So how does it do it? How does a computer get that physical MAC address when all it's got to work with is a logical IP address? You know, like 192.168.1.1. Well, the answer lies in this really clever little protocol. And this process is just brilliant. It's called ARP, which stands for Address Resolution Protocol. First, your computer basically shouts out to every single device on your network. It's a broadcast message. Then, the one device that actually has that IP address, in this case your router, it replies directly back, basically saying, "Hey, that's me. Here's my physical address." Let's look a little closer at those two messages. The first ARP request, that's a broadcast. Its destination MAC address is all Fs, which is the network equivalent of shouting to everyone in a room. But then look at the ARP reply. The destination is now the PC's specific MAC address. The conversation just went from a public announcement to a private direct message. Okay, fantastic. Clue number one is solved. Our PC now has the physical MAC address of our router, which is the gateway to the internet. So it can finally address that digital envelope and send the actual ping. Let's see what that looks like. So here it is, the first part of the conversation, the ping request. If we look at the headers, we can see the source MAC address is our PC and the destination is the gateway router that we just found with ARP. The IP addresses match up too. This is a direct point-to-point message, all happening right here on a local network. And here's the reply, the echo coming back. Notice how everything is just perfectly flipped? The source MAC and IP are now the gateways, and the destination is our PC. It's a simple two-way conversation, just like we expected. Case closed, right? Well, not quite. Because now comes the twist in our little investigation. What happens if we don't ping our local router? What if we ping a server halfway across the world? Something like, say, www.cisco.com. Does that digital envelope get addressed differently? So, let's just pause here for a second. We're about to send a message to a remote server. Logically, you'd think the destination address has to be that server, right? But which address are we talking about? The physical MAC address or the logical IP address? What's your guess? And here's the big reveal. This right here is the most important discovery of our entire investigation. I want you to look really closely. The destination IP address does change to the Cisco server's remote IP. That makes sense. But the destination MAC address, it's still our local gateway router. Why on earth would that be? This surprising little clue is what solves the entire case. It reveals the fundamental rule of how your local network operates, and it tells us the true role of your router. It's not just a doorway. So here's the crucial point, the thing you have to remember. Those digital envelopes we've been talking about, these Ethernet frames with their physical MAC addresses, they can never leave your local network. It's just not possible. They are only designed for local delivery, like mail that only gets delivered within the same small town. And this is how it all works. Your PC can't send a frame directly to Cisco, so what does it do? It sends it to the only device it knows that can leave the neighborhood, your router. Your router gets the frame, opens that digital envelope, takes the data out, and then puts that data into a brand new envelope to send it on the next step of its long journey across the internet. So let's just quickly recap what our detective work uncovered. MAC addresses, they're just like local house numbers. IP addresses, that's the full global mailing address. ARP is like the local directory assistance that connects the two. And most importantly, your router acts as the post office for your network, repackaging every single piece of data that's heading out to the wider world. And that leaves us with a final kind of provocative thought. If your router is the gatekeeper that examines and repackages every single packet you send to the internet, what else could it see? What other stories could it tell us about where our data is going? Something to think about. Thanks for joining the investigation. All right, today we're going to pull back the curtain on one of the most important but maybe least known parts of the internet, the data link layer. It's the silent workhorse that makes literally everything you do online happen, right from that very first click. So let's dive in and see what's really going on under the hood. Seriously, think about it for a second. You click a link and boom, stuff starts happening. Data starts flying from some server somewhere in the world right to your screen. But what is the very first thing that happens? Before your data can cross oceans or continents, it has to figure out how to get out of your own house. And that's where this unsung hero comes in. The data link layer is all about that very first step of the journey, getting data from your laptop to your router, and of course, the very last step, getting it from your router back to your laptop. It's the local guide for every single piece of data you send or receive. So, how does it get your data ready for that local trip? Well, you can think of it as part meticulous planner and part super efficient packer. It makes sure every little bit of information is properly addressed and wrapped up for its short but absolutely critical first hop. And to handle all this, the data link layer is actually split into two different sublayers. Each one has a very specific job to do: the logical link control, or LLC, and the media access control, or MAC. Okay, and this breakdown is super important for understanding how it all works. On one hand, you've got the LLC. Think of this as the planner. It's the software side of things, talking to the layers above it, like the network layer, figuring out what data needs to go. Then, on the other hand, you have the MAC. This is the packer. It's the hardware link that physically packages the data and controls who gets to use the Wi-Fi or the Ethernet cable. Now let's talk about that packaging. The data link layer doesn't just yeet raw data out there. No, it has to wrap it up nice and secure. This whole process is called encapsulation, and you can literally think of it as putting a letter into a very specific, very smart digital envelope. And the way it works is actually pretty simple. First, it gets a packet from the network layer above it. That's your data, that's the letter. Then it slaps a header on the front. That's the to and from address for this local delivery. Finally, it sticks a trailer on the end, which is kind of like a tamper-proof seal to make sure the data didn't get messed up on its way. This whole package, header, data, and trailer, has a special name. It's called a frame. And if we look a little closer inside that frame, the header and trailer have some crucial jobs. The addressing part, well, that holds the physical addresses for the very next stop. And that error detection field, it's got a special code, a checksum, so the device that receives it can double check that the frame arrived perfectly, with zero corruption. And this brings us to a super important point, the MAC address.
It's a unique serial number that's physically burned into your phone's or computer's network card. Think of it this way. Your IP address is like the full mailing address for a letter going across the country. The MAC address, that's the name of the specific person at the local post office who needs to handle that letter. Right now, it's only for local delivery, and get this, it changes at every single stop or hop along the journey.
Okay, so this layer doesn't just package data. It also has to play traffic cop. It needs to manage who gets to talk on the network and when, basically preventing a massive digital traffic jam right there in your living room.
And this is a huge deal. I mean, imagine you're on Wi-Fi at a coffee shop. You and everyone else are all trying to use the same airwaves at the same time. It's like a party where everyone's shouting at once. Total chaos, right? Nobody can be understood. So how do all those devices coordinate?
Well, back in the day, with old school wired Ethernet, the rule was something called CSMA/CD. It was basically listen before you talk. A device would listen to the wire, and if it was quiet, it would send its data. Now, if two devices sent at the exact same time, bam, a collision. They'd both detect it, back off, wait a totally random amount of time, and then try again. It's kind of like two people starting to talk at once, and they both go, oh, oops, sorry, you go first.
But with Wi-Fi, it's a different game. You can't always hear a collision happening in the air. So wireless networks use a much smarter system, CSMA/CA. The A is for avoidance. The device still listens for silence, but before it sends all its data, it sends out a quick little heads up that says, hey everyone, I'm about to talk for this long. All the other devices hear that, they set a little timer, and they politely wait their turn. It's way more organized.
All right, so we've got our perfectly packaged frame, and we've got the rules of the road. Now let's put it all together and actually follow that frame on its journey. We're going to focus on what happens when it hits a really important stopover point, your router. And here's a really important concept to grasp. Every single time your data packet moves from one network to another, like from your Wi-Fi to your internet provider's fiber network, a router has to do these 4 basic things. This happens over and over and over again on the path to where it's going. And this right here is where the magic happens. Your router gets the frame from your Wi-Fi, step 1. Then it rips open that digital envelope. It de-encapsulates it to look at the packet inside. Now the packet itself, with its final destination IP address, that stays the same. The router then takes that exact same packet and puts it into a brand new frame, a completely new envelope with new local MAC addresses, ready for the next part of the trip, maybe over an Ethernet cable. This constant unwrapping and rewrapping happens at every single hop. So, after all that, why should you care? Why does this one layer matter so much? Well, because it's the ultimate local expert. It handles all the grunt work that allows the global internet to even function. Let's just quickly recap its big jobs. It's the essential bridge between the abstract software of the internet and the real physical hardware in your hands. It meticulously packages our data into those frames for every local trip. It enforces the traffic rules to keep things from turning into chaos. And it masterfully handles that hop-to-hop delivery, constantly changing the envelope so the letter can keep moving. At the end of the day, it's really this simple. The internet speaks an abstract language of IP addresses and packets. Your computer and your phone, they speak a physical language of electrical signals and radio waves. The data link layer is the essential, tireless translator that lets these two completely different worlds talk to each other. Without it, the internet is just an idea with no way to actually touch the ground. So the next time you hop on Wi-Fi or click a link, just take a second. Appreciate the incredible, high-speed, invisible work that's going on. Think about those billions of tiny digital envelopes, those frames, being built, addressed, and sent every single second, just to bring the world to your screen. Pretty cool, right? Thanks for joining me on this one. You know, we spend so much of our lives clicking, typing, tapping, but what part of the internet are we actually touching? Well, it's called the application layer, and believe it or not, it's the only part of this giant complex thing that's built just for us, the users. So today, we're going to pull back the curtain and see how it all really works. I mean, really? Have you ever just stopped to think about it? You type in a web address, hit enter, and bam, a whole world just pops up on your screen. It feels like magic, right? But it's not. It's actually this super fast, perfectly choreographed dance between different programs and protocols. And that's what we're going to do today. We're going to break down every single step of that dance. So here's what's on deck. First, we'll figure out what this layer even is. Then, we'll look at how computers chat with each other. After that, we get to the fun stuff, how a web page loads, and what happens when you send an email. We'll wrap up by seeing how your device gets online in the first place, and then, tie it all together. All right, let's get right into it. Section 1. So what is this layer we keep talking about? The easiest way to think about it is it's the ultimate translator. Your web browser, your email app, they don't speak the language of network cables and weird router signals. The application layer is that crucial go-between. It takes your clicks and turns them into requests the network can actually understand. And then it translates all the network's geeky responses back into the stuff we see. Web pages, emails, you name it. Okay, so all this communication relies on something called protocols. And really, protocols are just a fancy word for a set of rules everyone agrees to follow. But before we get into the specific protocols, we gotta understand the two main ways computers can talk to each other. It all boils down to a simple question. Who's asking for stuff and who's providing it? So, on one side, you've got the classic client-server model. This is pretty much how most of the internet works. The restaurant analogy is perfect here. You're the client, you ask the server for something, like a web page, and the server brings it to you. Simple, right? But then you've got the peer-to-peer model, or P2P. This is totally different. Think of it like a potluck. Everybody brings something to the table, and everybody can take something. Every computer is both a client and a server, sharing stuff directly with everyone else. No central kitchen needed. Okay, so with that in mind, let's take that client-server idea and apply it to something we do, I don't know, 1 billion times a day? Loading a website. It seems instant, but there are actually 4 key things that happen. First, your browser looks at the URL you typed and just breaks it apart. It figures out what's the protocol, what's the website name, and what page you want. Step 2, it has to find the server. See, browsers don't understand Cisco.com. They need a number, an IP address, so it's got to look that up. Then, step 3, once it has the number, your browser sends out an official request, a GET request, asking for the web page file. And finally, step 4, the server sends back all the code, and your browser's job is to piece it all together into the web page you actually see. So that crucial step 2, looking up the number, is all thanks to something called DNS, the domain name system. And honestly, the internet's phone book analogy is the best way to describe it. You don't memorize everyone's phone number, right? You just look up their name. DNS does exactly that for websites. It translates the human-friendly names we use into the IP addresses computers need. Without DNS, the internet would be a nightmare to navigate. Seriously. Okay, so if DNS is the phone book that finds the number, then HTTP is the actual language you use when you make the call. It has a few basic commands. A GET request is the most common. That's just you asking to get a web page. A POST request is when you're sending something to the server, like filling out a contact form. And a PUT request is when you're uploading a file, like a photo. And hey, here's a super important pro tip. Always look for HTTPS in the address bar. That little S stands for secure. It means your whole conversation is encrypted, which is exactly what you want. Alright, so that's web browsing. Pretty cool. But what about something else we do all the time, like email? How does that work? Let's follow a message from the moment you hit send. Believe it or not, email is a team sport. It relies on 3 key protocols. First up is SMTP. When you hit send, SMTP is like the mailman who picks up your letter and takes it to the post office, the mail server. Now, to actually get your mail from that post office, you've got 2 options, POP or IMAP. And while they both retrieve your mail, they do it in ways that are, well, worlds apart. And this is the part you really gotta get. POP is like a classic physical mailbox. You go, you take your mail out, and now the mailbox is empty. POP downloads your emails to one device, and then poof, they're usually gone from the server. But IMAP is like having your mail in the cloud. It downloads a copy for you to read on your phone, but the original stays on the server. That's why with IMAP, your inbox looks exactly the same everywhere. On your phone, your laptop, your tablet, it's all perfectly in sync. Okay, so we're browsing, we're emailing, but wait a second. How did our computer even get an address to use on the internet in the first place? It can't just make one up, right? You guessed it, there's a protocol for that too. Yeah, say hello to DHCP, which I like to call your network's digital concierge. Think about it. When you check into a hotel, you don't just wander around and claim a room. The front desk gives you a key and tells you your room number. DHCP does that for your computer. The second you connect to a Wi-Fi network, DHCP is there to hand you a unique IP address and all the other info you need to get online. It's the unsung hero that makes connecting to the internet so easy. And it all happens with this lightning-fast 4-step conversation. It's kind of funny. Your computer basically yells out to the whole network, "Hey, is there a DHCP server out there?" That's the discover. A server hears it and replies, "Yep,
Here's an IP address you can have. That's the offer. Your computer then says, awesome, I'll take it. That's the request. And finally, the server locks it in and says, confirmed, it's all yours. That's the acknowledge. It's a little digital handshake that happens in the blink of an eye. Whew. Okay, we have covered a lot of ground. From finding websites with DNS, to getting online with DHCP, to browsing with HTTP. So let's take a step back and put all these pieces together. Let's see how this family of protocols builds that vital bridge between the apps we use every day and the network itself. This really lays it all out, doesn't it? You've got your key players, each with a very specific, super important job. DHCP gets you connected. DNS is your map telling you where to go. And then protocols like HTTP and SMTP are what let you have the actual conversations. It's this teamwork that makes our entire digital world spin. And at the end of the day, that's really the magic of the application layer. It's the reason the internet feels, well, human. It's this invisible translator that takes our simple actions, a click, a search, hitting send, and turns them into a language that computers can understand. It's what makes this whole thing work for people, not just for machines. And that brings us to a really interesting question to think about. We've got protocols for the web, for email, for sharing files, but now everything is getting connected, right? Our cars, our watches, our refrigerators. So what new kinds of conversations are they going to need to have? What do you think the next essential application layer protocol is going to be? What's the next big thing that will completely change how we live in this digital world? Today we're going to decode the secret messages your computer gets every single time an internet connection fails. We're going to find out what they really mean and how you can actually use them to your advantage. You know the feeling. We've all been there, right? You click a link and nothing. Just that little loading spinner going around and around and going absolutely nowhere. It's so frustrating. But what if I told you that your computer is getting messages back? Detailed error messages, almost instantly. The catch is, they're written in a secret language we're not supposed to see. Okay, so let's get into it. The key to understanding all these network headaches is something called a protocol. And really, a protocol is just a set of rules for communication. This particular one acts like the internet's own secret messenger, always working silently in the background. And that messenger is called ICMP, which stands for Internet Control Message Protocol. The best way to think about it is like the postal service for the internet. See, when you send a piece of data, you just hope it gets there. But if the address is wrong or the building's gone, the post office sends you that little return to sender sticker. ICMP does exactly the same thing for your internet traffic. It's important to note it doesn't carry your actual data, like your emails or the website you're loading. Nope, its only job is to report back and say, hey, that delivery, yeah, it didn't work out. So, what kind of return to sender notices does ICMP actually send? Well, let's decode a few of the most common ones. The most basic, most fundamental conversation ICMP can have is just about presence. Your computer sends out what's called an echo request. It's basically just shouting into the void, hey, google.com, are you there? And if that server is online and it can hear you, it sends back an echo reply that just says, yep, I'm here. It's the simplest possible test of connectivity. Now here's where ICMP gets really, really useful. A destination unreachable message isn't just one simple error. It actually comes with specific reasons. For instance, a host unreachable code means the entire computer you're trying to reach is just offline, gone. But a port unreachable code, that's way more subtle. It means the computer is on, but the specific application you need, like the web server software, isn't running. It's the difference between an entire building being empty and a shop that's just, closed for the day. Okay, this next one is, honestly, it's genius. To stop data from getting lost and just bouncing around the internet forever in some kind of endless loop, every tiny piece of it is sent out with a countdown timer. It's called the time to live, or TTL. Each time your data hops from one router to the next on its journey, that number goes down by 1. If that timer hits 0 before it arrives, the router that killed it just throws the data away and sends back a time-exceeded message. Now this is a safety feature, but as we're about to see, it can be used in a really clever way. So, we know about these secret messages, but how do we actually use them? Well, the first and most famous tool that speaks the language of ICMP is called ping. We're going to look at two main tools that use these ICMP messages. First up is ping, which uses that echo request we talked about to ask the simple question, are you there? And then there's traceroute, which asks a much more complex question. What was the exact path you took to get here?
Simply put, the ping command is our way of manually kicking off that ICMP conversation. When you open a tool like the terminal or the command line and you type ping google.com, you're telling your computer, hey, send out an echo request and just listen for the reply. It's a direct line to the network's most basic diagnostic tool. And this right here shows a really powerful troubleshooting process. By pinging different spots along the way, first your own computer, then your home router, and then a server way out on the internet, you can systematically test each link in the chain. It's a step-by-step method to find exactly where a connection is breaking down. But what happens if ping works, but your connection is still super slow or just acting weird? Well, that's where our second tool comes in. If ping tells you if you can connect, traceroute tells you how you're connecting by literally mapping out the entire journey your data takes. Remember that ticking clock we talked about, the TTL? Well, traceroute is this amazing utility that basically exploits it. It uses those time-exceeded messages not as errors, but as breadcrumbs to build a map of the network path between you and wherever you're trying to go. So check out how clever this is. First, traceroute sends a packet, but with a TTL of just 1. The very first router it hits sees the TTL, drops it to 0, and sends back a time-exceeded message, revealing its own address. Boom, we found hop 1. Then, traceroute sends another packet, this time with a TTL of 2. It sails right past that first router, but it gets stopped by the second one. Bam! We found hop 2. It just keeps doing this, adding 1 to the TTL each time, and building a complete map of the route, hop by hop by hop. A typical trace route might show something like 14 hops. Just think about that for a second. 14. That means to load one single web page, your data just passed through 14 different, distinct routers. In different buildings, maybe in different cities, maybe even in different countries. It's a rare and amazing glimpse into the hidden complexity of the internet. So when you put it all together, it becomes really clear that this simple little protocol is truly one of the internet's unsung heroes. I mean, think about it. Without ICMP, we'd be flying completely blind. It's the protocol that gives us all this crucial feedback when things go wrong. It gives us simple tools like ping to just, see if anyone's home. And it enables these incredibly clever tools like traceroute to map out the entire journey. Really, it's the foundation that makes the internet a stable, diagnosable network. So yeah, every single time you use the internet, this silent messenger service is right there, on standby, ready to report back if anything goes sideways. It's a fundamental, yet so often overlooked piece of the magic that keeps our digital world connected. So the next time a website won't load, don't just get frustrated. Remember, there's a story there, and now you have the tools to ask the right questions and decode the answers. The only question left is, what mysteries are you going to uncover about your own little corner of the internet?
Every single time you send an email or watch a video or even just browse a website, you're following a set of invisible rules. Rules you've probably never even heard of. So what are they? Well, today we're going to pull back the curtain and uncover the secret handshake that makes our entire digital world possible. To really get how the internet works, let's just forget about technology for a second. Instead, let's start with a very human problem. Imagine you're in real trouble, and the one single person who could possibly help you speaks a completely different language. How on earth would you communicate? All right, let's dive right into this idea of a communication breakdown. And we're going to use a scenario that I think feels, a little too real for some of us. So picture this. You're driving your new car. Everything's going great. And then nothing. The engine just cuts out. You manage to coast over to the side of the road, and there you are. Totally stranded. And the frustration is building. Big time. You whip out your phone, and with the last bit of battery, you find just one, repair shop nearby. It's your only shot. But as you walk through the door, you suddenly realize that your broken down car, it isn't your biggest problem anymore. Yeah, not a single person in the shop understands a word you're saying, and you don't understand them. The issue with your car is complicated. It was making a weird noise, sputtering, there was a light on the dash. How do you possibly explain all that? So what do? Seriously, think about it for a second. You can't just toss them the keys and hope they figure it out. You need a reliable way to get your point across. You need a plan. And that's exactly where this leads. Out of pure necessity, you have to invent a way to talk to each other. You're basically forging a common language right there on the greasy floor of the garage. And your plan would probably break down into a few common sense steps, right? First, you've got to establish some kind of basic language, maybe pointing or drawing pictures. Second, you break the big, complex problem down into small, simple pieces. And third, and this is crucial, after you explain each little piece, you have to confirm that they understood. You look for a nod, a thumbs up, something. It's just a totally logical way to communicate. Okay, now here is the big reveal. That simple, common sense plan you just came up with to fix your car, that is the exact same system, in principle, that allows trillions of bits of data to fly across the globe perfectly every single second. This brings us to the core of it all, the protocol connection. We're about to connect the dots and see how your frustrating garage scenario is actually a perfect mirror for the hidden rules that govern the entire internet. And boom, here it is. This chart makes the connection crystal clear. Your plan to establish a language is what the internet calls an application protocol. Explaining in small steps, well, that's the transfer protocol. Confirming they understand is the internet protocol. And the act of actually handing over the car for repair, that's the network access protocol. Let's just quickly run through what each of these really means. First up, the application protocol. Think of this as agreeing on the type of conversation you're about to have. When you're browsing the web, that language is called HTTP. When you're sending an email, it's SMTP. It's exactly like you and the mechanic agreeing that pointing at the engine and making a sputtering sound means my engine is broken. Next, you've got the transfer protocol, or TCP. You wouldn't try to act out your car's entire life story in one confusing gesture, right? You'd break it down symptom by symptom. Well, TCP does the exact same thing. It takes a huge file, like a movie you're streaming, and chops it up into thousands of tiny, numbered packets that can be sent one at a time. But how do you make sure all those tiny packets actually arrive, and in the right order? That is the job of the Internet Protocol, or IP. Yep, the same IP as an IP address. It acts as a digital mailing address and a delivery confirmation for every single packet. It's what ensures everything can be put back together perfectly on the other end, just like you waited for the mechanic's nod before explaining the next symptom. And finally, we have the Network Access Protocol. This is where the digital world meets the physical world. This layer governs how all that data actually travels over the hardware, the Wi-Fi signals, the Ethernet cables, the fiber optics. This is the equivalent of you physically putting the car keys into the mechanic's hand. It's the final step where the work can actually begin. So you see, when you stack all these protocols together, they create this incredibly robust, universal system for communication. It's what allows a computer made in Brazil to talk flawlessly to a server in Japan, even if they're running completely different software from different companies. Why? Because they've all agreed to follow the same common sense rules. And this really isn't just a technical detail. These rules are incredibly important. They are, quite literally, the invisible constitution that governs our entire modern digital world. So why does any of this matter to you? Because these protocols are the silent heroes behind every single thing you do online. They're the invisible backbone ensuring your email arrives, your video streams without buffering, and your messages are actually understood. They allow for this amazing interoperability between a mind-boggling number of different devices. Without this simple layered agreement, the internet as we know it would just fall apart. So the next time you go online, remember that invisible conversation happening behind the screen, that simple, logical plan ensuring everything just works. And that leads to a final thought. Now that you can see this hidden structure online, what other invisible protocols, what other unwritten rules are governing the rest of your daily life?
Hey everyone, today we are going to unplug the cloud. We're going to peek behind the curtain and get to know the physical reality of the internet, the actual, tangible, globe-spanning machine that connects all of us. So when you send a photo or stream a movie, what do you picture? Do you imagine your data just kind of floating up into some, fluffy digital cloud? It's a nice image for sure, but the reality is so much cooler because it's not magic, it's a machine. That's right, the internet isn't a cloud at all. It's a machine, a gigantic global machine made of countless physical parts. And today, we're going to see exactly how that machine works, right from the little chip inside your device, all the way to the signals that literally cross oceans. All right, so here's our game plan. First, we'll look at how your device physically plugs into this whole thing. Then, we'll get into the really cool part, how we turn digital bits into actual real-world signals. After that, we'll follow those signals through everyday copper wires, watch them ride beams of light, and finally, we'll catch them as they fly right through the air. Okay, first things first. Before a single piece of data can go anywhere, your device, your laptop, your phone, whatever, it needs a physical connection to the network. And that connection is made by a little piece of hardware called a network interface card, or a NIC for short. You can think of it as the physical front door from your device out to the entire world. So we've got our physical doorway, but what are we sending through it? Well, your computer only thinks in ones and zeros, right? A stream of digital bits. But you can't just shout a 1 or a 0 down a wire. You have to convert it into something real, something physical that can actually travel. So how in the world do we do that? Well, the first step is a process called encoding. The best way to think about it is like turning that chaotic stream of ones and zeros into a structured language, kind of like a digital Morse code. This makes sure that the device on the other end can actually understand what it's receiving, so it doesn't all just turn into a jumbled mess. And that brings us to the next step, signaling. Now this is the magic moment. This is where our digital data actually becomes physical. Those encoded patterns of ones and zeros get transformed into real physical energy that can travel through a medium. So what does that energy actually look like? It takes one of three main forms. It can be electrical pulses coursing through copper wires, tiny little pulses of light flashing through pure glass, or microwave signals radiating out through the air. Seriously, almost every single piece of data you have ever sent or received has traveled in one of these three ways. This is the physical backbone of our digital world. Let's start with the one you're probably most familiar with, good old copper wire. Chances are the device you're watching this on right now is connected by a copper cable at some point along the line. It's cheap, it's super easy to install, and for decades it has been the reliable, unsung workhorse of our local networks. But, being the common workhorse doesn't mean it's perfect, not at all. Copper has some pretty serious physical limitations that some very smart engineers have had to figure out how to solve. So, if it's everywhere, what are its biggest weaknesses? Well, it really boils down to three big challenges. First up is attenuation. Just like your voice gets quieter the farther away you are, that electrical signal gets weaker and weaker the farther it has to travel. Then there's interference. All sorts of outside electrical noise from power lines or even your microwave oven can mess with the signal. And finally, there's this thing called crosstalk, where the signals and wires right next to each other can actually bleed over and corrupt each other. It's like a garbled conversation. So how do we fix all this? Well, the solutions are actually pretty clever. To fight that signal fade, attenuation, we just put strict limits on how long the cables can be, usually about 100 meters. To block interference, we can wrap the wires in a metallic shield. But the solution for crosstalk is just brilliant. We take pairs of wires and simply twist them together. This twist ingeniously causes the interference from each wire to cancel the other one out. It is such a simple, elegant fix to a really complex physical problem. And here's a perfect example of that shielding in action. If you've ever had cable internet, you know what a coaxial cable looks like. See that woven copper braid? That's not just there to make it stronger. That is the metallic shield we were just talking about. Its whole job is to protect that main copper conductor in the middle from all that disruptive electrical noise. But what if you need to go way faster and way farther than copper's 100-meter limit? Well, for that, we have to ditch electricity and start using light. We turn to fiber optics, sending our data as tiny pulses of light down strands of pure glass that are as thin as a human hair. This, my friends, is the internet's Autobahn. And the advantages here are just massive. Because we're using light, fiber is completely immune to all that electrical and radio interference we talked about. This lets it carry way more data. We're talking much higher bandwidths over incredible distances. We're not just connecting rooms in a house anymore, we're talking about connecting entire cities, countries, and even continents with massive cables laid on the ocean floor. This table really just says it all. I mean, just look at the distance. Copper maxes out at 100 meters. Fiber can go up to 100,000 meters. That's over 60 miles without needing to boost the signal. It's not even a fair fight, and the potential for speed is at least 10 times higher. Now, the trade-off, of course, is the cost. It's much more expensive and difficult to install, which is why we don't have fiber running directly to every single desk, at least not yet. And that brings us to the final piece of the puzzle, the one that gives us all our mobility, wireless. Instead of electrical pulses in a wire or light pulses in a cable, we use radio and microwave frequencies to carry our ones and zeros right through the air. This is what finally untethers us from the wall and lets us connect from pretty much anywhere. Which, of course, leads to a really important question. I mean, think about it. Wi-Fi feels like the default for everything now. It's everywhere. So if wireless is so convenient and so capable, why on earth do we even bother with all those messy copper and fiber optic cables anymore? Well, the answer comes down to its own set of physical limitations. Wireless signals get blocked by walls and other objects. They get disrupted by everything from your neighbor's Wi-Fi to your own microwave oven. Because they're just broadcast into the air, they are, by nature, less secure. And maybe the biggest one you've experienced, wireless is a shared medium. Everyone connected to a single Wi-Fi hotspot is sharing the exact same pool of bandwidth. And that's why the Wi-Fi in a crowded coffee shop can feel so painfully slow. So here's the big takeaway from all of this. There isn't one single best technology. It's just not that simple. The internet is a hybrid, a team effort. We use powerful fiber optics for the massive, long-haul backbone of the internet. We use cheap, reliable copper for the final stretch into our homes and offices. And then we use convenient wireless for that last little hop to our phones and laptops. Each one plays a critical role, solving a different piece of the puzzle. So the next time you hear someone talk about the cloud, you can smile because you know what they're really connecting to. A machine, an incredible physical machine that sends your data as electrical pulses, beams of light, and invisible waves. It really makes you wonder though. Our data travels by wire, light, and air today. What's going to be the next physical medium for our digital world? Thanks for joining me for this one.
Have you ever stopped to think about how the internet really works? Not the websites you see or the shows you stream, but the invisible magic that's happening behind the scenes. Well, today, we're going to pull back the curtain on one of the internet's most crucial, yet totally unsung heroes, the transport layer. Just think what you're probably doing right now. You've got this explainer playing, right? Maybe you have an email tab open, a big file downloading in the background. All of this data is flowing through one single internet connection. So how in the world does your computer know which data packets are for this video, which are for your email, and which belong to that huge download? It's a fantastic question, and the answer lies in one very, very clever layer of the network. So that clever layer, it's basically the internet's traffic cop. It's the part of the system that prevents total digital chaos, making sure every single piece of data gets exactly where it's supposed to go without getting all mixed up. Its official name is the transport layer. And honestly, the best way to think of it is as the shipping department for your computer. Now, it's not worried about the physical roads or cables the data travels on. That's a whole other layer's job. Nope, the transport layer's only concern is creating this logical, organized connection between an app on your machine and an app on some other machine, no matter where it is in the world. You know, at its core, it's really got three big jobs. First, it keeps track of every single conversation your computer is having online. Second, it takes these big chunks of data from your apps and chops them up into smaller, more manageable pieces called segments. And third, on the other end, it meticulously puts all those pieces back together in the right order. It's the ultimate digital organizer. Okay, so this shipping department, it's not a one-size-fits-all kind of deal. It has 2-star employees, 2 main protocols, and each one has a very different specialty when it comes to moving your data around. So let's meet them. On one hand, you've got TCP, the Transmission Control Protocol. Think of TCP as the super reliable, certified courier who triple checks everything to guarantee your package arrives safely. And on the other hand, you've got UDP, the User Datagram Protocol. This is your speedy messenger who's all about getting the package there as fast as possible, even if it's not absolutely perfect. They're built for completely different things. TCP is for stuff like email and websites, where every single bit of data is critical. UDP, that's for things like live streaming and online gaming, where speed is everything. All right, let's zoom in on our reliable courier, TCP. This is the protocol that makes absolutely positively sure your most important data arrives intact without a single byte out of place. The real secret to TCP's reliability is that it's connection-oriented. What that means is, that's a little formal. Before it sends any actual data, it insists on setting up this dedicated, two-way connection. It's just like making a phone call, right? Both people have to pick up, say hello, before the actual conversation can start. And this connection is what allows TCP to make some really powerful guarantees. It ensures reliable delivery because the receiver has to send back a little confirmation called an acknowledgement for every piece of data it gets. If the sender doesn't see that confirmation, it just sends the data again. Simple as that. TCP also slaps a sequence number on every single packet, so even if they arrive all jumbled, the receiver can put them back in the perfect order. And get this, it even manages the speed, telling the sender to slow down if it's sending data too fast. It is incredibly meticulous. So how does it set up that formal connection I mentioned? Well, it performs this very polite 3-step dance to make sure both sides are ready to roll. This whole process is famously known as the 3-way handshake. First, your computer sends a message with a SYN flag. That's short for synchronize. It's basically asking the server, hey, you there, can we talk? The server then replies with a SYN ACK, which says, yep, I'm here, and I acknowledge your request. And finally, your computer sends back one last ACK, confirming, awesome, connection established. Only after this polite introduction does any data actually start to flow. Okay, now let's do a complete 180 and talk about our second protocol, UDP. If TCP is the careful, meticulous courier, UDP is the fire and forget speed demon. UDP is connectionless. What does that mean? It means it completely skips that whole 3-way handshake thing. It doesn't set up a formal session at all. It just takes the data, puts a simple label on it, and yeets it out into the network. That's why it's called a best effort protocol. It gives it a good try, but it makes 0 guarantees. So what does that actually look like in practice? Well, no handshake means way less waiting around. If a packet gets lost in transit, UDP doesn't care. It's just gone for good. If packets arrive out of order, that's the order the application gets them. Now, this might sound totally chaotic, but the upside is incredibly low overhead. UDP is lightweight, simple, and because of that, it is blazing fast. But hang on, why would you ever want a protocol that might just lose your data? Well, because for some things, a tiny bit of data loss is a totally acceptable trade-off for raw speed. Think about a video call. Would you rather have the video freeze completely while it waits for a lost packet from 3 seconds ago to be resent? Or would you prefer a tiny momentary glitch while the conversation continues in real time? For applications like video streaming, online gaming, and voice calls, speed is absolutely king. Okay, so we've got our 2 data movers, TCP and UDP, but we're still missing a piece of the puzzle. We still haven't fully answered that original question. Once all this data shows up at your computer, how does it know where to go? How does it find its way to Chrome instead of, say, Spotify? The answer is a really clever system called port numbers. And I love this analogy. If your computer's IP address is its street address, then port numbers are the specific apartment numbers. See, every application on your computer that needs the internet gets assigned a unique port number. This tells the transport layer exactly which door to deliver each incoming packet of data to. And to keep things from getting totally chaotic, a lot of common services use these standardized, well-known port numbers. For example, standard web traffic pretty much always goes to port 80 using TCP. Email is typically sent using port 25. And DNS, the system that turns website names into IP addresses, often uses UDP on port 53. This whole system acts like a universal address book, making it super easy for computers all over the world to find the right services. So when you put it all together, that seamless experience you have multitasking online is actually this incredible digital ballet. It's an amazing juggling act of thousands of ports, with TCP making sure your downloads are perfect, and UDP making sure your video calls are fast. And all of it is managed perfectly by the transport layer to make sure not a single ball gets dropped. And that brings us to a final, really interesting thought to chew on. For decades, the internet was built on the rock-solid reliability of TCP. But as more and more of our lives move online, demanding real-time video, cloud gaming, instant communication, we're seeing this massive shift towards speed-focused protocols like UDP. It leaves us with a fascinating question for the future. In this constant tug of war between speed and reliability, will the need for speed eventually just win out for good? It's something to think about the next time you're juggling a dozen tabs online.